I thought you didn't want to sit by. I got it.
Okay.
Hello. I don't have.
So we're getting the YouTube live stream up. Okay.
I didn't want to sit by. I got it.
So we're getting the YouTube live. Okay. There we go. All right. So, okay, so Dan is getting his laptop hooked up. And he'll be ready to go here in just a few moments, I think.
I think so.
Yeah.
Can you make me like bigger so everyone can see me?
Yes, I will make you the man, and I'm going to mute myself. And then we will share your.
Can everybody hear me?
Well, yeah, I think that.
Yes.
Okay.
Can everybody hear me out there?
Yes.
Oh, shit.
Yes, yes, nicely.
How do you know?
They should raise their hand or something.
Raise your hand if you can hear me.
Yeah, I've muted myself. No, you turn down your speakers, and you don't have to. Okay, so where would I go? You're computer. Yeah. Yeah. Oh, that's easy. They don't mind me. Too complicated.
Well, I don't know.
I'm gonna try that, and we'll unmute the TV and see if that works.
Hello? Hello?
Are you muted, Dan?
No? Can everybody hear me?
I can hear you.
Yes,
Turn my
yes.
volume up.
Coming through to New Mexico.
Hello?
Yes, here.
What's that? You can hear us?
Yes.
Okay, good. All right, fine.
Yeah, it's just coming through your computer.
Okay, so I'm going to share my screen. Can I do that now?
Yes, you should be able to.
Okay. I wasn't prepared to go right now. We were going to test it out first, and we didn't get a chance to do that.
Right in the middle of the bottom thing.
Yeah, but I'm not ready yet. I have to go to the presentations and open it. I'm not going to share my.
Howard, can you make him full size? Howard, can you make him full size? Full screen?
I'm pretty much full size.
Hit escape. Yeah, and hit escape. Hit escape.
No, I just got to go over to the. I got to go over here, and now I can share my screen. But I wanted to share just.
Maybe it's aspect of the bottom.
Have you got your presentation?
The presentation is right here.
Okay, so hit share screen,
Say speak.
hit share screen.
I did.
Okay, and then you should see your presentation up here somewhere.
Lots of pictures. Whiteboard.
So next year, somebody can give a presentation on how to run Zoom. Okay.
Yeah.
Every day that's gonna work, but I still don't.
Why isn't
I
it
know,
there?
I've had trouble too.
Well, it's one thing being a participant, and it's another thing running
Like
it.
that.
Oh, isn't that it right there?
Because I'm on a Zoom call.
No,
every
this
week,
is it.
so
This is my
I'm just
application. Okay.
One of the people.
Now here, I want to share that.
That it,
Well, it doesn't seem like it. That's
all-
Howard's.
Yeah.
Bruce Howard's.
Should be able to share your screen.
Well, can I share the whole screen?
Yeah,
How do I do that?
I think you just hit that.
All right, sorry, everybody, I'm so
Okay,
lame.
Great.
Uh,
Now, if we'd asked you to design a telescope for us in 3 minutes, it would have been a different.
I know how computers work. To believe it, I could make one out of transistors. But I don't know how to do this. Now, how can I get this thing up so that it's off?
Pretty much there.
Yeah,
Look at the screen.
Yeah, it's the aspect ratio of the.
Oh,
difference
up
aspect.
there, it's okay. All
Yeah.
right, okay, fine. Does anybody recognize this?
I do.
No,
Looks like a 3-in-1.
Yeah. And we're talking to Oyinata in New York, New York University. Dr. Valerie, and I can't think of her last name. Wanted to get this telescope to work. They've had it for years, and it's the largest telescope in New York, she told me. And it doesn't work. It won't track. They still use it, just kind of pointing it around once in a while, but they wanted to upgrade it. You can see it's got a little, if you can see my mouse, that little hand controller there, but that only works on equatorial telescopes, and it doesn't work on, this is in the early 2000s. Anyway, she wanted us to upgrade it, and so we gave a proposal, but it was too much money because we had to make too many parts. And so she said, well, we have somebody here that can make the parts, or maybe I suggested it, I don't know. And so that's what happened. Their machinist, Alan, I'll think of his name a little later, his last name, and he made all the parts except for 2 that I'll show you in a minute. So this is the azimuth, and if you can look at my mouse, this is a gear. This gear is stationary. This is the motor, and it's got a little worm gear in it, and then it goes down, and there's a spur gear that makes this azimuth go around, and there's some rollers under here. Whoops. That's the azimuth motor. This is the existing. And it actually works, but they wanted a new one, so we designed this up. This is kind of a close-up. We bought these new Pittman motors with no reducers, and then we got this you can't see it on the screen.
No,
Okay.
you can show it after you stop sharing.
Okay, I'll show this stuff later on to you Zoom land people. And this is a 50-to-1 harmonic drive. And then we made a gear on the bottom. You'll see that on the bottom pretty soon. We're also putting on Renishaw encoders. So we provided the encoders. We provided this adjuster, reed head adjuster, and that's a 200-millimeter ring, and it's very accurate. So this should turn this telescope into a really nice professional telescope, especially if they ever can afford a rotator. And this is another view. It's pretty simple, and he's already made all this stuff, and Alan, and this is the CAD drawing. This shaft, which is in orange, was solid. And I said, well, before this was done by a battery and they didn't have any wires on it, you're going to need wires. You need power and USB. And so Alan took this orange shaft completely off. He drilled 3 holes, right, like for mounting this, so that this ring holder would be perfect. And he bored a hole all the way through it. This is an exploded view. You can see the 3 holes here and the 3 holes on this green plate, which it's not really green, but this is the underneath. There's a shaft that goes all the way down. There's no bearing down there. It's just a hole. And this is God, I can't remember what this stuff is, but it's got a nice CTE that kind of matches the ring. And it's a lot easier to machine than stainless. So he built all this stuff. I think he 3D printed this yellow part. Here's the under part of that same little thing that I was showing you earlier. And so this is still going to walk the telescope azimuth around. Now we're going to the altitude, And this is the altitude gear, and this is actually a clutch, so we're probably going to lock it so they can't use the clutch anymore. This is a face-on view of the clutch, and here's the existing motor that moves the altitude. And you can see the teeth clearly there. And this is a battery that's there now that we'll be deleting that. Now, everybody here that's been looking at this boomerang, now you can see what it's for. And it holds the reed head, and we have a similar arrangement on this encoder ring, but we had to get the reed head way up there. So, and the reason we made it out of steel instead of aluminum is because of the CTE. We didn't want it to get closer, you know, it's lower than aluminum. And it's got a similar arrangement. And this is the motor bracket. And Alan had me design it and split it up so he could glue it together because his 3D printer wasn't big enough for it. So then he tested it out on the telescope and it fit pretty well. So, and that's it for the first part. This is supposed to be about radio telescopes, but it's actually 3 projects. One is a prospective project that I hope we can do. And so some of you might have, oh, I wanted to tell you, I did have a conversation with Jim, what's his last name? Jim, I can't think of it, Jim Burr. And he was helpful and he was appreciative that it was going to be fixed and working, and it was really nice. He's in his 80s, I think, and it was a good conversation. And I found out the pitch of that gear, which is I wouldn't. I'm doing this all remotely because they couldn't afford to fly me out there to test to check it out. All right. What's that? Yeah. Yeah, it's pretty free. Yeah. Yeah, I love it.
And kind of 2 questions regarding drive gears like that. When I built my go-to, I was advised to use a timing belt on the azimuth, and it kind of has a tensioner and wrap around and all that. And I was somebody, it wasn't you, but somebody said, nah, don't try to use that timing belt and put your gear right up against it, because you'll get a bunch of, well,
Yeah, that could have been me.
probably you, yeah. The comment being that it would just walk out of the teeth of the gear. And I'm see, but you're doing just exactly that here. How does that work?
I don't know what you mean.
Oh, well, then I'll get you later. Because maybe it's a subtlety between a machine gear and a timing belt. I don't know. But
How do we keep the gear from going up and down?
or walking out of the teeth and just skipping a tooth or
Oh no, it won't happen. I mean, unless it's not centered at all, but I'm pretty sure it would be.
yeah, that's what I used.
Yeah.
So okay, I'll get you later.
Okay.
Thanks.
Any other questions
Yeah.
about this one?
Aperture was-
It's a 40-inch. Oh, and by the way, it's got a flat secondary and then a tertiary that comes out, so you don't have to get up on a ladder. I've never looked through one, but I'm expecting a nice dark, out of focus, dark spot in the image of a star.
Secondary looks like it's maybe 20 inches or so.
I think something like that. Yeah,
Okay.
yeah.
What do they plan to do with that?
Well, she does likes to do galaxy stuff. I can't remember now, and they also like to do exoplanets. Yeah, and they'll probably get into satellites since the software duck works so well with that. Okay, so any questions from Zoom land? Guess not. Okay. So this, oh, back up. Okay. Vishnu Reddy, Dr. Vishnu Reddy from the University of Arizona, got 2 radio telescopes, and the purpose of them is to do astrometry. It's not like listening to satellites. It's for tracking satellites, and they don't do any communication with it. They just listen to the radio frequency, and then they can tell where the satellite is. And it's not nearly as accurate as optical, but you can do it in the daytime when it's raining. also, maybe you can't find it with and you'll be able to find it with a radio telescope. So that's the whole purpose of these. It's kind of a new experiment, I think. This is Biosphere 2, and right over here is the observatory. And this image was taken before they had the radio telescopes. It's just right about, whoops, oh well. It's right about in here, they put the radio telescopes. And this is you never know what you're going to get there. I've been there about 4 or 5 times and I love going there. It's just fun. Here's the 2 radio telescopes.
What was, that was just some lynxes?
Yeah, or bobcats, yeah.
Bobcats.
Yeah. So this is a small one, the 2.4 meter right in the foreground, and in the background is a 5.3 meter. And they all have double worms. So if you can see my mouse, here, this motor turns a worm, and that turns another worm gear, and that worm gear, this worm turns a worm gear, this worm turns another worm gear, which turns the telescope in azimuth. They all have that except for this altitude uses an Acme thread. So this one is going to be very nonlinear, and I found out, let's see, we'll see that. Oh, getting out of order here. So what this is going to be, it's a 1 pixel camera, the radio telescope is. But so what we're going to do, we're going to settle on 4 or 3 squared and take images of and so we'll make our own image. So then we can do astrometry, or they can do astrometry with where exactly that beam is. And it's going to be nonlinear because of this thing. So I'm going to have to do a little math so that when I control the motor, it's going to control the same as the encoder feedback, which we'll get into a little bit later. And I found out that the laws of cosines will solve this pretty easily. And I made a little spreadsheet and checked it out. And so the math is in hand. And I'm not a mathematician, but you know, me and the internet work out pretty good sometimes. So I have to put those in our SciTech EXE software and, you know, put in, so we can put in the links and the threads per inch and all that stuff. So, and here's another image of it. So this is the altitude motor, and every motor on all 4 motors, they all have a reducer on here. And then that goes into the shaft of the worm. In this case, it goes into the shaft of the nut, the Acme nut. So, okay, I already mentioned this, and there's plenty of backlash because we took the motors off and then we turned the shafts, and it's really easy for, you know, quite a long time. And then you can feel it start turning the telescope. You go the other way, it does the same thing. And so I'm going to have to put backlash in the Force 2 controller to compensate for that as best we can. And all right, so what I did first was I looked at the horsepower of all the motors, and then I turned that into a torque value, and I've come up with these huge motors and reducers with reducers on them. But then when I visited the site, we carefully measured the torque of every one by using a lever and a spring scale, and it's way less than I thought. And we were able to eliminate all of the gear reducers, every one of them. And the only one that needed a bigger motor, they're all using the same, pretty much the same size motors, except for the altitude for the 5.4 meter. It's you know, it's not balanced, so you have to lift it up. So that one takes a bigger motor, but still it doesn't need a reducer. So we're going to be able to slew a lot faster. Here's the existing gear reducers that we're eliminating. This one in particular, the 2.4 meter altitude, is a 10-to-1, and then after that is the Acme thread. And I'll show you the slew speed. It's unbelievable. But this is one of the motors for that small telescope. It's a 1/4 horsepower, and it's a 10-to-1 ratio, 480 volt and 720 RPM. And this is unbelievable. So Vishnu and the university bought these telescopes from England, a company in England. Turns out they were made in China. And can I say the S word?
Go for it.
Stupid.
Yeah, stupid. I mean, so you guys probably know what these are. They're solid state relays. So you can turn the motor on and you can turn it off. And they're induction motors. That's the other thing. They are induction motors. And if anybody knows anything about induction motors, you know you can't really position them very well. You can, if you have a VFD, you can sort of position them. A VFD is a variable frequency drive, so you can change the frequency. Like we use 60 hertz, so instead of 60, we can use 30 or 40 or whatever and make it be any speed. And so, you know, you could do a little better with a VFD, but still, you would never try to position a telescope of any kind with an induction motor, and that's what all these 4 motors are. In the case of the 2.4 meter, they're not even VFDs. They're like relays. Okay, go fast. Okay, we're there. Go shut it off real quick. I mean, that's what the software, their software does, I guess. So what were they thinking? I said.
So Dan, with the red controller, you can't control them.
Yes, I looked into that. And there's two VFDs that sort of work.
No, there's actually another way to do it with amps and phase control.
Yeah, I read up on them on it, and I decided against it. And
I've seen a 20 horsepower induction motor modeling a quartz watch.
Okay. Well, you know, I mean, I'm not saying it's impossible, but
It costs us
okay, interesting. All right. Okay, this is what's really kind of cool. 0.077 degrees per second. That's how fast the altitude on the 2.4 meter slewed. And the reason they did that is because of the problem of, hey, let's turn them on and off, and then we can get it close, and it's going to stay right there, or you can just kind of predict a little bit the deacceleration, and then it stops. You can't track. There's no way you could ever track a satellite that way. But anyway, 20 minutes to move from the horizon to the zenith.
Yeah.
This is one of the encoders. I put it sideways so that I could get more of a picture on it. And there's limit switches. There's 4 encoders, one for each axis on the 2 telescopes, and they're absolute encoders. They're magnetic. We looked up the specs. Their accuracy is 1/4 of a degree. And that's the beam width, according to Vishnu. That's the beam width of the radio transmitter, or that's what they can see. The beam width is, what's that?
The field of view.
Yeah, yes, I think so. Okay, what were they thinking? So we decided to replace those with Renishaws, and all you in Zoom land, I'll show you the prototype when we're done with this. With when I turn out my camera on, I have. So this is what we came up with. So there's the encoder read head, the one in the cyan colored, and then the blue colored is the encoder ring. The darker purple is made out of Delrin, and the pinkish is all made out of Delrin 2. And we just eat all that out with our NC mill and drill all the holes, and it takes about a half an hour. And then that's with the lid on it, and you can see the shaft sticking down at the bottom. This is exploded view. So there's really only 4 parts to make, including the lid at the top. All right. So this is the 6 point, what did I say? 6.4 meter, right?
I think you said 5 points.
5.3, that's right. This is the altitude axis, and this is the one that uses the biggest motor. I think this one is a 3 horsepower motor. But again, it's a double worm, and it's, so we don't need nearly that. It's got a 10-to-1 reducer on it, 3 horsepower motor. This is an azimuth. And this is a control box. So you can see that little hand controller there. No, that's not a Celestron hand pad. It's just go this way, that way, or the other way. That's all it can do. And those are the 2 VFDs. You can see my mouse. This is one VFD. That's the other VFD, variable frequency drive. The rest of it, I'm not sure what all of this stuff is, but it's mostly all going to go. This up here is the radio receiver and all that. Now you can write lots of books about what I don't know about that. So that's all up to them, but they say that's not a problem for them. So I'm okay with that. We're going to use our Force 2 because of the big motors. Here's an installation we did in Chile. I think about almost a year ago now. You like those electrolytic 3D printed electrolytic capacitors, those purple ones? And then that's a bridge rectifier down there at the bottom. I'll put my mouse on them. So these are electrolytic capacitors. This is a bridge rectifier. That's a power supply. We're doing a similar thing, but we'll buy real ones. Now, the reason we we had to ship this before we got the parts. So we 3D printed parts and wired it. And then when I went down there, I brought the parts with me and put them in. So that's another story. So this is one of the motors that we're going to put on there. This is a Siemens motor. It's pretty powerful. And we're making this. I'll show you this orange part. I have one with me. And then we have these blue plates cut, but we have to machine them. And let's see if this movie works. So this is one of the motors. We just got them late last week, and so I hooked it up. And now it looks like it's going slow, but it's not. It's you know, the interface between the frames per second and there, now it's slowed down. So let's see.
It's a brushless DC.
Yes. And that's it for the radio telescopes. We're going to probably, they want to do it in November, so this coming month. We have one of the guys that worked for us for a lot of years. His name's Daniel. And we taught him how to run machines. Well, we hired him to work on the grounds. We have a lot of acreage. And then he went to work for Sidereal Technology out there. And he learned how to machine, how to weld. He learned how to program machines. I mean, he's, you know, about young man, about 30 some. And some other company stole him from us. And so we did all that training and he went to another company. Can you believe that? I mean, and the company that he went to is here, TMS, which is our mother company anyway. So, I mean, it's all good.
Still his boss.
I'm still his boss, but you know, when they really need him on a ship on the East Coast, you can't say no. So we really struggled to get work done on that, but he's going to be back next week to work at Sidereal. So we're hoping to make a lot of progress. So anybody have any questions about this?
So the customer for this project, did they have a realistic idea of where they're starting and where they want to end up?
Well, that,
Obviously they're going to end up like way better, but what is their,
what a good question. And I don't know the answer to that. Talking to Vishnu, they misled him. They thought this is going to work perfect right out of the box. They can do all this stuff. And they spent weeks over there, and Vishnu called me up. He was angry. I mean, really angry. Yeah, I don't know what they're going to do, but we're going to make it work.
What kind of slew rate are you gonna get out of these scopes?
Well, for instance, that one that was 0.077 degrees per second, it's going to be 0.77 degrees per second, roughly, because we're not going to have a reducer on it. And we could go faster if we use higher voltage, and we could do that. If they wanted to go faster, we'd have to, but I doubt if they'll want to go faster. We're running at 170 volts DC.
I have a question outside of your purview on this. I noticed that those smaller radio dishes they have extremely fast F ratio, like they look like they were F.25 or something.
Very well could be, yeah.
They almost look like the nose of a bullet or something.
You want to go back and look at it real quick?
Yeah, they're really deep.
What would they use these for? Is it to collect data?
Astrometry. That means finding out where they are in the sky. Yeah, that's really quite amazing, isn't it? Really, both of them.
Extraordinarily fast.
Yeah.
Fish.
Well, dishes usually are, I mean, faster than.
Well, the bigger ones were way more shallow, but these guys are like, they're deep. I'm just guessing F.25 or something.
Or less than that. That's actually a lot faster than that, I think.
That's what?
Faster than that, I
Oh, really?
think, yeah. I don't know that, I don't know what it is, but I just pointed. So we're gonna have accurate encoders, we're gonna have a lot faster slew speeds, and we're gonna have software, you can use SciTech EXE, probably many of you know you can track satellites with, and so it's just gonna work, Okay, I just learned a new word yesterday, Victorian engineering. And that was from Howard Banich, because I showed him some of my pictures or something, and I was telling him how amazed I was at the technology in the 1890s. So I have before we go on to this third project that we do not have a purchase order for, we've just done a preliminary report, and that's all we've done so far. And we've also made their telescope work. You'll see that story in a little bit. But this is the largest refractor in the solar system. I asked John Briggs yesterday, and he said there might have been some other attempts. He said the only successful. And so, well, maybe I put that in here. Thanks to John Briggs. And this is the telescope. Does anybody recognize this? That's right. This is what John Briggs was talking about, which was a wonderful talk. I just enjoyed that so much yesterday.
Oh, there's Einstein.
Yeah, I was looking at that.
Yeah, there he is. Okay, so they want to refurbish this, and this is Dr. Amanda Bauer that's in charge of it. This whole observatory now is the Yerkes Foundation is a nonprofit organization that owns it now and operates it. And Dr. Amanda Bowers is the head of the telescopes and everything like that. And they want to do two things, and they're both pretty big jobs. Actually, item one is a lot harder than item two, but even item two is going to be, some challenges. And I got to say again, this is not for sure. This is an idea. They flew us out there, several of us, and you'll see us all later on. And but I would bet that we're going to do it. That's my guess. But don't go around saying that we got the job, because we don't. And there is going to be some tension between the cosmetic restoration and making it work well, because we're going to have motors sticking out there. If they want it to work well, we're going to have motors. And Amanda wanted to have all the old handles, like for the clamping, you turn it and tighten the clamp and all this stuff. She wanted to have it look like that. So maybe we can have fake handles. I don't know. That's not my department, okay? If you took a look at my desk, I should have put a picture of my desk in here. But incredible engineering, Victorian engineering for 1890s technology, push buttons and contactors, and some meters and things that were just coming out back then. I'll show you a picture of the motor later on, one of the motors. And they have tangent arms. I made a tangent arm in my early 20s or 30s when I was 20 or 30 years old for my little Meade German equatorial mount, and so I could guide in declination, I mean, so this has been around a long time. And then the clamps for transferring one to the other. And slewing, it's amazing. Also, I have a video of it slewing. It's quite amazing. And then, but the nice thing is on the right ascension, they do have a worm gear, a huge worm gear. I mean, it's huge. And I want to take advantage of that because then we can, you can leave it there for cosmetics if you want, or you can take it off. The tangent arm we won't need, the clamping system we won't need, and we can do everything with the worm gear. And I hope we can do that. Right now, if you see that little green circle there, that's a function generator, which is just a thing that puts out a square wave or a sine wave or whatever. They're just putting out a square wave. And here's a close-up of it. And that's the frequency 4186. And that I looked at, I did the math and it looks right. That goes to this little thing, which is just a stepper driver and it has a pulse input. But that thing has been up there. I've been looking at this telescope for other reasons. We upgraded the other two telescopes there. And so I got a chance to look at this, and that function generator has been there for years. John Briggs probably knows when it was put on. I don't know the answer to that question. But it's been there for years, and that's their sidereal tracking. They can't adjust it. If they want to go faster or slower, they have to run up there and turn the knob. This is a stepper motor, the back of it. And what's that? Yeah. Yeah. There's not a bellows coupling, but it's a coupling. And this is kind of an overall, this tells you how it works. The stepper motor goes in there, turns a small worm, which turns the worm gear, which turns the big worm, which turns the great big worm gear. Oh, this is another movie. Side. Cool. There's looks like 100 teeth on that worm gear. Worm gear. There's 360 teeth on the worm, the main worm. Yep. All right, so we plan to remove this stepper motor and put in a powerful brushless motor, and we'll be able to slew at 1.5 degrees a second, which is what we timed it. The existing is 1.5 degrees a second, and I do want to check with John Briggs to make sure he thinks that this is a good idea. But my only fear would be if that gear is not made to slew for long terms of slewing. So I'll be asking John about that.
I saw ropes on that telescope yesterday. I have a feeling all the time they just pull a rope.
Yes, there's clutches on it, and right now the declination motor, the gear is stripped. It's a fiber gear, and so the only way they can use the declination is move it by hand. Okay. So right when we left, and then Ralph Nye stayed one more and worked with Amanda, and then the tangent arm on the right ascension stopped working, and that's terrible because you basically can't use a telescope because you can only kind of move it, but it's so powerful you can't line it up by hand. You have to use push buttons, and so it's really frustrating. So it became useless. I don't know what was wrong. They didn't figure that out. But we have a step and direction controller, and that little electronic device I showed you earlier has step and direction inputs. And so I talked to Amanda, and she was okay with it. We loaned her a controller, and so it's working now. And now she can control it with push buttons, just like the old tangent arm, but it's done with speeding up and slowing down or reversing that stepper motor. And this is our step and direction controller. And we're only using one axis, of course, just the right ascension. And I worked with him online, and we went it as fast as we could safely go and not stop, spinning because of the low torque and stuff. And there's another story, but I'm not going to go into that one. This is one of the tangent arms. This is a right ascension tangent arm, I believe. Yes, I said declination, but I think that's the right ascension. And if you can see my mouse, well, actually, there's a close-up. So this motor is a fine guiding thing. So it's a shaft, and then that turns this gear, which turns this gear, which turns this main shaft. And then the course is this motor, which, you know, pulls it or pushes this tangent arm. And that's just, this is a slow motion, or the, I guess, I call it pan mode. Most people call it set. And I can't remember, set and guide or something. Anyway, on the declination, we are gonna have to use this, because we can't, the gear train for the declination, it starts out inside of with a motor I'll show you, and then it goes up through all these bevel gears, and then one of the bevel gears has a special angle, so it goes up the right ascension shaft in the middle of the shaft and turns another bevel gear, which turns the declination. And it is lots of backlash and no doubt a lot of periodic error. And so we'll probably move it, do some software where we move it to where it's supposed to go, roughly, and then we'll probably use this motor. Well, not this motor. We'll put on another servo motor that will position it, but we only need one because we can control the speed. Yeah, this is the one that we're going to use. I kind of said everything that's on this page. So I first went to work at the shipyard in 1986 or so, and there were some ships, Matson ships, that still used direct current for all their motors on their ship. They had direct current generators and direct current motors. I don't think there's any ships like that anymore, but I learned a lot about direct DC motors. This is a shunt field, if you can see my mouse. There's probably a series field. Maybe this is too old, because this is 1890s is when, well, look at the nameplate. That kind of says it all. Yeah, except for it only tells me the voltage. It doesn't say the amps. I wish it would have. But I did measure the current, and it comes out to be, if you go by the standard 750 watts per horsepower, and it was 10 to 15 amps, that comes out to be about 5 or 6 horsepower. But those motors were very inefficient compared to the brushless motors we have today. And so we're not going to need nearly that. So that's what I want to do, is replace that motor that I showed you, that stepper motor, get rid of that, or maybe put another reduction on it. We'll probably need another reducer on it, but not that first worm gear. We'll go directly and turn the main worm gear, and we'll be able to slew and track and do whatever.
And that Westinghouse motor that you just showed us, that, yeah, that thing, is that on a boat or on the telescope?
That's on the telescope.
Okay. How big is that?
Let's see, I should have put a quarter. I'm guessing it's about 24 inches in diameter. Yeah.
It's inside the pillar. You climb
Yes.
up the spiral staircase and go in a door, and it's in the same like little room where originally the weight-driven governor, gigantic weight-driven governor for the sidereal tracking, was located. This is tucked in the back of the room, and of course it's gigantic and amazing.
Yes, thanks, John. Hey, John, since we have you, when did they put the stepper motor on? Do you know?
Man, I might have put it on.
I
yeah.
wouldn't be surprised.
Yeah, because I did a fair bit of work on earlier incarnations of the of sidereal tracking, and but it was in the very early 90s, and it's I fear that it's hard for me to remember. Yeah, but I made changes to the motor, and there were earlier incarnations, but a lot of a lot of what you were showing in the pictures was very familiar hardware to me
I
from
know.
early
I
days.
knew
Yeah,
that.
yeah, yeah.
I'm really glad you're here.
Well, I certainly look forward to speaking with you about this in the future. It's of
Yes,
course it because it's close to obviously close to many of our hearts. It's simply so cool.
yes, yes. What?
How long do you operate with the weight?
Oh, somebody asked Joe asked, how long did that weight clock drive run the telescope or track the telescope?
That's a very good question because it astonishes me that they physically removed the gigantic governor mechanism from the room that's like 3/4 of the way up the iron pillar inside the pillar. It would have been a lot of work taking that out. Maybe it facilitated access to these motors here, having the clock mechanism out of the way. That might have been the justification for getting rid of it. But I was always mystified why that big clock mechanism was not in storage somewhere in the building, because it was not. And it's a great mystery what became of it. Maybe somewhere buried in the director's reports is a clue to what happened to the mechanism. But it was such a cool mechanism, it's not something you'd want to recklessly throw out. And I don't know how soon they got rid of it. Because interestingly, the weight driven governor for, say, the Mount Wilson 100-inch continued to be used really right up until Carnegie shut Mount Wilson down in the early 1980s. And it had a reputation for working really well for the 100-inch. So, so I just don't know when the weight drive was retired at Yerkes time. Wish I did.
Yeah, so that's interesting. Now, I was there with I can't think of his name right now. So that we went way down, where that huge motor is that raises and lowers the floor.
Yeah,
And
down at
cabinet,
yeah.
there's a cabinet there, and he told me, and we opened it up and looked, and there's a bunch of gears, and I have a picture of it. I'll send it to you.
Yeah, I know
And-
that. I know I can visualize it because those have been sitting there a long time, but there would have been so much more to the
Right.
mechanism as well.
But
And
he told me that those were the gears for the clock drive. So I guess they have the gears, and we have some drawings from original drawings still. So
Yep.
it's possible somebody could
yeah, was that Ed Struble? Was this a guy who had previously worked there? Ed Struble. Maybe
We-
showed you those gears.
do it.
Is everybody familiar with the WW?
Yes, that was Ed. Yeah, thank you. Yes, he was there when we went there. When we went there in June, he was there. He was one of
Yep.
the people. He's
Good.
real great. Okay. And I know you, John, I know you recognize this because you did it a long time ago.
No, I worked on these, but I don't take credit for installing this
Okay.
improvisation. But these guns took the place of the manual clamps, so they engaged and disengaged the clamps built into both of the tangent arms, and
Yeah, and they work. I don't know how long ago they were installed. Do you, John?
I actually think they might have been installed back in the 1960s when there was a major re-engineering. I hesitated to say upgrade, but there was a re-engineering of the Yerkes telescope when a fellow named Van Altena was on the staff. He was an astrometrist who ended up not staying on the University of Chicago faculty, but he went on to Yale. But a great deal of modernization was done to the Yerkes telescope in this period, and it was, in my view, it was controversial because people would tend to throw out a lot of the earlier manual ways of controlling things, maybe a little bit too recklessly. And these guns were very powerful, and they tended to possibly to damage the mechanical clamps that are internal to the tangent arms. And I don't mean to go getting lost in the weeds of the telescope details, but there's a lot of history here, and I fear that the new people at Yerkes don't necessarily know as much about the history of these changes as perhaps they should in the ongoing decision-making process. So I hope to help however I can.
Yes, you will. You'll be a big help. What was I going to say about this? So these are, what do they call these things? Not jackhammers, or
They're like, yeah, what they're like for
impact
impact
wrenches,
guns.
yeah.
Yeah, impact wrenches. And
Yeah, so you're right.
Yeah.
It really bangs it, and plus it's really loud.
yeah,
Okay. They're off now.
That's
Okay,
called
they're on, now turn it off. Yeah. On.
that's called disturbing the peace.
What am I exactly looking at?
Well,
What am I doing?
that turns a big. Probably John can explain it better.
yeah. I'll try. So the telescope has manual clamps to basically engage to clamp the telescope to the moving polar axle, for example. You could originally, you could move this telescope by hand, and you'd unclamp it and grab hold of the eye end, and you can walk it around, and you can set it and point it purely by hand. And but if you want any of the slow motions to work, or if you want the clock drive to work, there are not friction clutches on this telescope, but there are mechanical clutches that are maybe reminiscent of the mechanical locks that you might have on something like a Bridgeport mill when you want to, lock various things on a Bridgeport. And so originally, those clamps, those locks, were all actuated from hand wheels that were geared and shafted down near the eye end of the telescope, and it was like really cool mechanical stuff. And you wouldn't you wouldn't injure the internal bronze blocks that are doing the clamping deep inside the mounting when you're tightening them by hand. But when they decided to re-engineer it in the 1960s, they took a lot of this mechanism off the telescope tube. They lightened the telescope tube. It probably had less flexure as a function of that lightening. But when they put these stupid things on there, man, they were really hammering on the internal bronze blocks, and they've had to take the whole thing apart once or twice to repair damage deep inside the mounting. And there's a machinist retired in Williams Bay who actually was present when some of this work was done. And he's the guy they really ought to be talking to understand what some of the problems are inside.
It's pretty easy.
John, so I have an idea to replace this with a brushless motor that has a reducer on it, and then use software and use a current sense to know exactly when it is. And so we don't do this hammering crap. So
yeah,
and they would be quiet too.
Yeah, no, you're on my end. The film did not fully testify to the noise these things make. And I mean, this thing was still, when I started on the staff there in late 1990, they were still taking parallax plates and things with this telescope, and it was still very much in use as a photographic telescope. And man, like late at night, the shutters open. The observer, who is actually a guy from Finland, who'd previously been some kind of a merchant marine captain or something. He'd be up there, and you'd hear these guns go off. Anyway, I forgive I'll stifle myself, but you're bringing up interesting memories. But
well, John's right about that. It's an echo chamber in there, and when these go, it really is. You know, you really should wear earplugs to protect your ears. It's that bad. All right, this is getting near the end. This is a movie, and you'll see Ralph Nye. I'm sure you know him.
Oh yeah.
So that sound is the right ascension slowing, and we don't know where that noise is coming from, but that's noisy too. But that gear train is quite extensive, so there it comes. That's 1.5 degrees a second. I timed it.
That scope has a huge bonus, so I said, yeah, a lot of wood.
Yeah, you know, this engineering for the 1890s, absolutely marvelous, if you ask me. Let's watch Ralph walk by. I was just trying to look at the dial so I could time it, and he walked right in front at the wrong time.
Instead of the right ascension circle, it's more of a meridian circle. It goes from 0, 1, 2, 3, 1 way, and then 0, 1, 2, 3.
Right. Yeah. So it's not an hour angle in that sense. Yeah.
It is actually, well, it's an hour angle that measures relative to the meridian. The meridian is 0, and no matter what side of the pier the telescope is flipped on, it reads. It'll work. Yeah, it works surprisingly well.
Yeah, that's the early versions of SciTech EXE did it the same way until I got yelled at by somebody saying that's not how everybody does it. So so these are some of the existing controls that they did in the 60s, I think.
Exactly.
And this is you know, when we're there with this cardboard thing of Einstein was, and I if I'm in there working, and then I look up, who's that? You know,
Einstein or Benito Cycles. That's a good one.
This is me. That's Einstein. I forget Amanda's daughter's name. That's
Vivian Hetty.
Vivian, thank you. That's Ed Struble, and this is Ralph Nye from yes, he completely rebuilt a wonderful telescope at Lowell. Okay.
Cool.
No questions.
When will you know if you get
I don't know. I haven't talked to Amanda since we got it all working with the step and direction controller. And so I'm just patiently waiting. I'm glad it's not right now. We're kind of busy, so.
That's pretty cool to be glued into something that historical.
I really hope we get it because that's one of the reasons too, you know.
Well, I hope you do, because maybe next year we could have the workshop there and
wouldn't that be cool?
Yes.
Yeah, I've looked at the trapezium in this telescope. Yeah, that was pretty cool. And this is just in for art. I know John knows this guy.
He's my neighbor.
Yep. Yeah.
I'll just make some quick comments that Eric Toops, who's an electrical engineer by training, but very interested in optics and solar observing, he discovered this telescope in a New Mexico junkyard lying in the dirt, it completely disassembled as a big pile of parts that had been literally dumped there by a dump truck. He was able to buy the whole thing for 40 cents a pound. The optical tube assembly had not been taken apart. It was a 24-inch f4 with an optical window in front. He reassembled it, and with the help of Dan's control system, the first night they turned the control system on and got a pointing model Eric was able to track satellites with that instrument, which he has named Eagle because it looks like the Eagle lander on the moon. So that's a fabulous story, and I hope Eric shares it with this group some future year.
Oh, wow.
It's amazing.
You know where it came from?
Oh, good. That's what that's what the telescope looked like before Eric got his hands on it. No exaggeration. He rebuilt the the servo motors. And it was absolutely astonishing what he accomplished to make it, and it works. So, and there's Dan's control system making it real. And yeah,
That's
amazing.
another Force 2. And then this is the first light image.
Got the supernova.
Yes,
Right.
I think it's right here.
Yeah.
I think so. Amazing. Absolutely amazing. We're very proud to have Eric in the neighborhood here.
Yeah.
Yeah, good job.
He bought a school. He lives in a school. Unbelievable.
Continuing education.
Did we go over?
Not really. It's a few minutes.
Okay.
Yeah.
Well, let's see. I'm gonna log out of here if I can figure out how. Might need some help.
Stop sharing your screen.
That was good, Dan.
Yes.
It was fun. Okay, Zoom meeting. How do I get out of this? Leave.
Anybody there? Anybody there?
Yeah, we're here.
Okay. Ready for me to start?
Just one moment, please. Dan's gonna do a little show and tell.
Okay.
Yeah, sure. Yeah, for some reason I can't get on full screen, but you'll be able to see
Okay.
right in here.
Can you help us do full screen for Howard? It'll be a lot better.
Well, I mean, I'm selected to be full screen.
Okay. Okay, let's see, where does this? So if you remember that 3D drawing of the encoder, this is the block of wood that we did for testing our CNC, and it worked fine. So you can see the little encoder ring in there, the bearing at the bottom. Here's the bearing at the top for the lid. Oh, come on. There. And they go together. You can see the little ridge on there with radiuses. That goes on there. It's sort of like that. And then this is one of them that we did. Daniel did finish, but it just needs a plate, and we need to drill the holes. That's for the radio telescopes. And, yeah. Okay, now we're going to the JMI. That's one of the reducers. We bought 6 of them and only need 2. This is aluminum. We just had a water jet because we could do it a lot cheaper than them. That's that part that E3 depended for the test. And this is the boomerang. So I'm going to test it right now, see if it comes back. Here we go. Ready?
Yeah, look out, Grace.
Okay. Thank you.
Okay. All right. So thank you again, Dan. And next up is Bruce Howard. His talk is about 24-inch Altaz Cassegrain. And I'll let him share his screen. You should be able to do so now. Oh, I see Russ has joined us. That's good.
Does everybody see my screen?
Now we do, yes.
Okay, good. So, let me get to the first slide here. Yeah. Today I'm going to talk briefly about my 24-inch cast screen that I built over the last years and put into operation a couple years ago. It's a lot different than some of the telescopes I saw at the presentation last year in that it makes no pretension about being mobile. It's big and heavy. It weighs about 1,100 pounds. And it shoehorned into this 10.5 foot, 12.5 foot ash dome here. And in this picture, it's actually at work. I turned the lights up just briefly to take this picture. And you can see the basics of it is an Aldaz design with an open truss and a fork type mount. I got some better pictures a little bit later on. And these are the things I'll touch on during this. The specifications of it, the design goal, construction, how it fits into the dome, and just a brief introduction to my SETI instruments and ancillary equipment, which are all homemade. And then I'm converting it to direct drive motors at this time. One's done and one's under construction. And hopefully with a little help from Dan, I'll get that going later this year. Here's some general views of it here. This is the back plate here with one of the two instruments that I use. It's bolted to the back plate. It's solid to the back plate because the focus is done electrically by moving the secondary mirror. And you can see the general construction of it here. These boxes in the back on the wall there, this one has the side Realtek drive, and one of the others has some of the ancillary electronics that work with these instruments. And then there's another box, dome control. The dome control is pretty important because the width of the slot is only slightly bigger than the mirror. So it has to be within a degree or so in order not to do any vignetting. And then this is the primary mirror mount, and I got some better pictures of that later on. This 24-inch cast screen is sort of fast for a traditional cast screen. It's F12, which works fine for me because I do all the science with the principal ray. It probably wouldn't be too effective for wide imaging. The coma off axis becomes pretty severe, but it works fine for me. Originally, when I started in this telescope, I got a quote for a custom 24-inch mirror and cast screen set, and it was prohibitively costly. But fortunately, the optician had a 24-inch mirror that he made for another customer, and it fell through. And he was able to perforate that, refigure it, and make the secondary at this F12 system for a much more modest cost, which made this project possible. So it's a 24-inch mirror. It's F3.4 in the primary. The secondary is 6.5-inch diameter. Even at F12, the focal length is real long, 288-inch. It's Aldaz telescope open truss with an 18-point whiffletree type mount. The focus is 16 inches in back of the plate, which gives me plenty of room to put the instruments there. And it's 28 arc seconds per millimeter on the scale. The drive right now is more of a traditional system with worm gear and servo motors. Like I said, that's going to be replaced here this winter, this spring maybe. And the focus is on a motorized mirror, which is really required because the instrument package is relatively heavy and it would not be possible to hang it from a focuser on the back plate. This works much, much better. And as I mentioned before, it's heavy. It weighs about between 1050 and 1100 pounds. Here's an overall view of the machine. Starting at the bottom, this is the azimuth drive, which a portion, a matter of fact, the majority of it is actually below the observing floor, which is itself is about 3 feet off of the ground. And it has, right here is the main bearing package, which is massive taper roller bearings back to back and then preloaded to remove play. There is no like plate and balls or anything on it. All the load and the azimuth axis is taken by roller bearings. And right here, this is where the Renishaw encoder is, right close to the fork. It was 1,200,000 counts. Now it's 30 million counts, which will work well with the direct drive. And then down here is a traditional worm drive that I have some detailed drawings of it. The fork and the main tub here are constructed out of 1/8-inch cold finish steel and then reinforced with angles and square tubing to stiffen it up and raise the natural frequency. The same thing for here. The tub contains a mirror mount and the mounting plates for the truss. All these things were fabricated by welding and then sent out and had them machined to where they'd all be dead square and parallel with one another. You can see a little bit of my instrument package here. It actually passes through the bottom. Not really necessary, but it does. The Altitude drive, same thing, a 16-inch worm gear with a Renishaw encoder. There's one of the Pittman stepper motors. Then there's a 3-to-1 belt and then 360-to-1 on the teeth.
Yeah, Dan has a question for you.
Excuse me?
Dan has a question.
Oh, okay.
Hey, Bruce, are those the same encoders that you used before and they're incremental?
They're incremental encoders, yes.
Yeah, okay. All right.
I wish I had those other ones, the ones that are, what are they, 60 million? And then they remember where they are, they're absolute encoders.
Yeah, well, we'll talk about that later, Bruce.
Yeah. I'm going to definitely need some help getting that Force 1500 tuned up to drive these things, that's for sure. In the top here, we got the truss tubes. These are chromoly tubing with a thin wall. I like the steel tubing because the CTE is half of what aluminum is. And then up at the top, this is an octagon ring fabricated from thin-walled steel tubing also. And here's the focus mechanism. I have a much more detailed picture of that later. And these plates are steel too. I didn't want to make them out of aluminum. Here again, the coefficient of expansion, I like for it to be the same, keep some tension on this. Here's some of the methods of fabrication. This is the fork being built. I had these side plates cut at a fabrication shop. I guess they used a plasma cutter to do these. They're 1/8-inch steel. And then I built this table with double layer of 3/4-inch fiberboard, which is real flat. And you can see I put holes in it so I could clamp this down and measure and make this exactly what I wanted. Then I tack welded it all together and then raised it up and completed the welding on it. There's miles of heliarc welding in this fork and also in the tub assembly too. Then after this was all welded up, then an 1/8-inch steel plate was on the inside and outside to complete the fork. This is a view of where the main tub, you can't see the mirror right now because these safety covers are closed. They're made of 1/4-inch plastic and they have a little magnet on it. When you open them up, they register against the truss. And here you can see the entire structure. It comes within inches of the top of the dome. It really is a shoehorn fit into the dome. That's how all these things were made. And here's the mirror mount. Originally, when I started on this project, this was going to be a fork mounted equatorial. That's why if it was only LDADs, I would have done the radial support a little bit different. But you can see it's a standard type 18-point mount. And these pivot on a steel pin and then Teflon bushings in here. So it's completely free in all axes of motion. The radial supports here, this internal hexagon ring is machined out of aluminum, and then it's connected to the actual clamps out here with these rods, and these are made of Invar, which is a nickel alloy with a 0 coefficient of expansion. And if you add up all these things, it more or less equals the expansion of the mirror. So I can keep these things pretty tight, and even with a large yearly change in temperature, keep the gap pretty small here. The mirror itself had a relatively small hole in the perforation, so the baffle tube had to be reduced. It's, I think, 3 inches here or more, 3.5, and then it's reduced down, and it goes through and into the backplate, and it can be independently collimated in the mirror with the spring-loaded assembly. Here's some details here of the upper section. This ring fabricated from steel tubing. All these parts, after they were fabricated, they were machined flat and then bead blasted and painted at an automotive shop. So it's a pretty durable paint job on here. Same thing with the tubing here. This is the mechanism that focuses it, a little bit bigger detail here. I have a detailed drawing coming up, but basically it uses a stepper motor, a ball screw, and then a bunch of rollers that guide it so that it's free in the Z axis, but absolutely constrained in the X and Y axis. And this will allow it to focus even with a 600 power eyepiece. You'll see no shift whatsoever. A star just blooms, goes back down to about as sharp as it'll get, and then blooms again on the other side of focus. And these are some details of it. It's got limit switches to prevent over travel. Here's the focus mechanism. This was generation 2, and the one in the machine is generation 3, but there's very, very little difference. See, the motor's up top driving this ball screw, and there's sets of 4 rollers at 2 different elevations. On each elevation, 2 rollers are fixed, and then 90 degrees to them, there's a pivot roller. That's what this die spring does. It rotates around this pin and it pushes the roller up against the cylinder here. The cylinder has been machined with 4 flats that are precision ground. So that's what locks it in to the X and Y axis. And then of course it's free to move in the Z. It has 20 millimeters of travel, although that's only a third of that is actually needed. And then down here, we've got the secondary mirror, and it's collimated with die springs and nuts. There's 3 die springs, 180 to 120 degrees apart, and then brass nuts here. These are really potent springs, so there's no locking mechanism. You just tighten and loosen one at a time and to achieve the collimation. Here's the existing drive mechanism. Got the Pitman motor, got a 3-to-1 ratio on a tooth belt coming up here. The worm gear is this entire assembly right here, the worm gear, the motor, and so forth. It pivots on this bearing over here, and you got a release handle. It's kind of like a gear shifter on a car. And this entire mechanism will pivot, and it releases the worm from the worm gear to do the balancing. That's what this lever here is for. This is the same motor I think that lots of the Scitech installations use. It's a 10-to-1 ratio. Here's a detailed picture of how the existing drive works. This is what I was describing before. It pivots here, and then this Teflon block has a tongue and groove to lock this side up, make it stiff. And then this release handle will pull this entire mechanism down, and that allows it to be focused. I put a plexiglass cover over to keep the dust off of it as much as possible. This little spring here maintains this in the lock position until you push it over, and then you can pull that down, release it. Torsion spring. Here's how it all fits in the dome. As you open it, the grate is right about here. You open the door and go up these stairs. This is the actual observing deck. As I was mentioning before, the bulk of the azimuth drive is underneath the floor here. The azimuth drive bolts up to this couple yards of concrete here, goes down the ground, gives us a really, really solid mount. And it also having the floor here puts the instrument package at a convenient height. No ladder or anything is needed. So that the double advantage of having the floor off of the ground. And you can see in this picture how close it is. It's just a few inches away. Just fits in this dome. Shoehorned in there. Oops. Here's the azimuth drive over here. This is the section that bolts up to the this is the mating part for the fork, and you can see the encoder here and the reed head here, and this is all made of aluminum plate that's been anodized. And down here is the mechanism. It's very similar to the one on the altitude drive, just a few minor geometry differences to fit on here. And here I am, I'm lowering it down into the floor, and these bolts are the ones that are coming out of the concrete pier. And then once I got it down there, I used a machinist level to make it as flat as possible. And here, this is a crane. These pieces were so heavy that it was not possible for me to manhandle them into the dome. So I had this crane come out. The guy was real good. He dropped all these pieces down through the hole. It was well worth the $300 he charged me to save all these parts from destruction. I was very pleased with that. This is a couple years ago. Matter of fact, 2 years this month that I put it all together. Here's the mirror and the mirror mount and the installation technique. The mirror is sitting, this is this permanent mount in the back plate here, and it's sitting on this little cart with 4 casters. And this is a temporary fabrication from plywood and 2x4s. And once I get it on there, I slide it underneath, and then with these all threads, it gets jacked up into the final housing and tightened up. There's, I think, 18 bolts that hold the back plate up against the main portion of the tub. The pointing and tracking accuracy, because it's so heavy duty, it's pretty good. This is a 5 arc second circle in here, and almost all the stars are in there. The RMS error is less than 3 arc seconds, and these are all over the sky. Yeah. I'm going to talk just briefly about my primary instrument, and it's a heavy instrument. Oops, went too far. This is the overall view of it and the interior of it. This device uses 2 photomultiplier tubes. The incoming beam comes in, hits this beam splitter, 50% or less losses, but go to one tube and 50% come down to this other tube. And this whole thing works on the premise that a laser signal would activate both of them simultaneously, where the starlight alone, the photon arrival rate is slow enough to where only one tube would be tripped at a time. And this mirror is on a stepper motor to where I can observe it through this eyepiece, which I don't do much anymore because I have this camera. But in previous iterations, I used this to target it. And then this stepper motor pulls this mirror out of the way. And then the beam goes into the detection technology. This picture here, this device is over here, and it moves several different aperture sizes into the optical beam. There's a 10 arc seconds, 20, and I think 40, and then wide open. So depending on the scene, I can select the appropriate aperture. A lot of this is similar to what photometry was like in the photomultiplier day. Of course, that's been almost totally replaced with CCD photometry. And down here is a custom circuit that I built it analyzes all this and reports it to a computer. And then this here's a regular camera, commercial CCD camera. And then this device here is similar to this. It's a motorized mirror that deflects the beam up into here, and then it shows up on a computer screen with a crosshair. And that's really how when I move it from star to star, how I ensure that it's found the right star and tracking properly. It doesn't have a big view, 8 arc minutes, but that's plenty since the stars are usually within arc seconds of the command. This has a separate focus mechanism independent of the main focus mechanism, and that's this over here. And it works like the main focus. There's a stepper motor, a lead screw, and ball slides here that move the camera up and down over a very short range. And this is the other component in my in the instrument section. This is a filter wheel. It's not much different than a commercial one, but I made it much heavier duty because it supports the weight of those heavy instruments. It has neutral density filters in here because those PMTs, photomultiplier tube, are easily swamped by a bright star. Anything brighter than about magnitude 8 has to have some attenuation put in it. So these filters go from 50% passband down to 1%, and I can dial them in. The stepper motor turns this gear, and then this Hall sensor produces a start position, and then it just counts pulses as it commanded. And here's the dashboard on my primary computer. This, of course, is the Sidereal Technology arrangement up here. And then this is the view of my CCD camera with the crosshair in the middle. And these are softwares that I've written to control this controls the instrument package, and it has the star selection and the high voltages for the photomultiplier tubes. the actual count rate here, some time here, and this section here controls the neutral density filters, and this focuses it. This down here is for the dome synchronization. As I had mentioned before, the width of the slot and the mirror size are not that much different, so it's important that it stays synchronized. The Ash Dome came with just a conventional 1/2 horsepower induction motor and a reversing switch. It's kind of crude. It moves too quick. I took that motor off and put an AC servo motor and encoder on it and a home switch. So now it'll synchronize. You push one of these buttons to initialize the dome. It goes to a home position. And then from there on, the encoder provides the information about where the dome's at. This software hooks up through ASCOM to the SciTech and extracts the azimuth, and then it compares it with the desired position and operates the servo motor to keep the dome within 0.4 degrees of where the telescope is pointing. And this application, all it does is move the primary focus. And as I mentioned before, I'm building the direct drive motors. I'm going to install them, hopefully, maybe in December or January. They use Dan's Force 1500 controller. One's done, not tested, or done, and the other is in an earlier stage of construction. You can see here, they probably look a lot like the ones you've seen before. There's 24 coils and 32 magnets. And there it is on the test stand. I'm getting close to trying to fire it up, and I'm gonna need some help from Dan to do that. And that's really what I got. Any questions?
Yeah, Dan has a bunch, I think.
Yeah.
Okay.
So my first question was, on your secondary, it looked like a Pitman in your 3D model.
Yeah, that was a second generation. The newer one uses a stepper motor with an electric brake. The stepper motors are on all the time and get hot. So how it works is when you focus, it releases the brake, it moves the lead screw, and then the brake is released after that.
Okay. My next question. Gosh, I should have written it down. I might think of it later on, but my last question is, do you need a job?
If I was a young guy, I would jump on it, believe me, because it would be more interesting than the work I used to do, designing pumps for nuclear reactors.
Hey, this is Jeff Bolden. I'm curious, who did your optic work?
Star Instruments.
Oh, Flagstaff?
Well, the guy moved, I'm trying to think of his name, Paul Jones.
Yep.
He moved, I think he's retired now, but prior to that, he moved to North Georgia. Maybe had family members there. I bought a 16-inch mirror from him in like 95 or something, and I had used that telescope until this one was finished. And the mirror quality is on that 16-inch was really good. This one is good too, but it doesn't, because it was so big, I had to make some compromises to keep the cost to what I could afford. It's not made of low expansion glass. The 16-inch was made of Astro Cetal, which was a Russian version of Zerodur. And that is good to have the low expansion glass, but it's something I couldn't do on this one.
Thank you.
Yeah, Paul Jones made the 32-inch mirrors for the Fairborn Observatory, our original photometric telescopes, when he was located in Flagstaff.
I picked my 16-inch mirror up at his works in Flagstaff. Like I said, I think it was in the 94 or something like that. And he had a lot of really neat stuff there. He has the test equipment. The Cassegrain mirror would be very hard to home make. I bet Mel could no doubt make one, but it's a big job because you have to have a lot of test equipment. The secondary isn't spherical, and it takes a real expert to get that to the right.
Yeah,
quality.
he made our mirrors for us back. He made our mirrors for us back in the 80s. He was just kind of getting started then. Anyway, they were excellent quality and very reasonably priced.
Yeah. He was a very good optician. I think he's retired now, but I could be wrong about that.
I have another question. I remembered my question that I forgot. You mentioned that the time delay for the laser to the star light was different, and that's probably because of the position of the planet. And it could be before or after, depending on where it is in its orbit, or simultaneously. Is that right?
Well, the way that detection works, it's looking for a laser signal, and the idea of it is that a laser could outshine the sun for a very brief time. And lasers exist right now. They use them in the fusion research that could outshine our sun by four orders of magnitude. Now, of course, it's at one spectral line and for picoseconds. So the way that instrument is designed, if you're looking at a 10th magnitude star, you get about 1 million counts, which is 1 microsecond between photons. They're not regularly spaced because of the quantum stuff, but so 1 microsecond apart, and this thing is looking for 5 nanosecond arrival. So you never see that unless there's a glitch or something. One tube fires, the next tube fires, not coincident. If that big, huge group of photons from that laser arrived, they would be spaced so close that within that 5 nanosecond window, that both of those tubes would trip, and that would be called a coincident arrival. That's what that circuit board looks for. It has super fast amplifiers. They write 1500 volts per microsecond, and they go into a comparator. So if it's approximately 5 nanosecond, if it comes in within that time frame, both of those tubes will trip, and then it'll show up on the dashboard as a coincident arrival. That's the principle behind that camera.
Okay, I'll have to think on that, or maybe I'll discuss it with you later. But
Yeah.
have you had any coincidence?
Yeah, I've a few, but if they don't repeat, then I can't say much about them. My software includes an algorithm that looks for repetition, and they would have to repeat because the power company could turn the generator on, lightning, airplane go by. There's a lot of potential causes for one event. So it would have to be more than one event. It would have to be a pattern of them in order to say that that was something important. And that happened one time, and I never repeated. And I thought maybe it was something with the airplane strobe light or something, but it was exciting when it happened.
Yeah, I'll bet.
What signs of artificial intelligence are these telescopes for?
Could you hear that question?
No, I couldn't. I'm sorry.
What optical signs are you looking for with these telescopes?
It's the whole idea of it is this optical SETI looking for a transmission from an intelligent society. You've heard, of course, a lot about the radio SETI, which is the big thing. This is something different. It's been done on the professional level some at the Lick Observatory. There was a team there in the past that did it with equipment, something like what I'm using. So that's what it's looking for, is this simultaneous arrival of a powerful laser signal, which would outshine the sun, the sun at the transmission location. That's the whole principle of it. So what I do is I bring it to a potential star, and I have a catalog from potentially habitable places, and I get it on there. I turn it on. I let it run for 10 minutes. It does a scan. The scan lasts 10 minutes, 600 lines, and each line is about 900 milliseconds. So there's a lot of scans, and each scan looks for one of these arrivals, and then the software keeps track of that. And I can go back to the software real quick. Up here, these are the count rates, raw count rates from the 2 tubes. And then this one is the coincident count. And the reason it's showing some is if you look at this, it's all, any of these that end in an 11 are a test flasher. A signal from the a GPS receiver, they have one, a square wave that's coincident with 1 second. The rising edge of it is within nanoseconds of a UTC second. And I wire that into my test circuit. So every 1 second, it goes into there and it counts by 100. So there's 100 seconds between every one of these test pulses. And that tells me that the system is working as designed, because the test pulse is very short, 8 nanoseconds, and very weak, just enough to trip the tube. So if this test signal comes in every 100 seconds, I know this system is working properly and would make a detection if there was anything to detect. That's this section of the software up here. I turn the scan on here and it runs for 10 minutes. Anytime I want, really, but I usually run it for 10 minutes. And they're made. This one was one that was interesting because there was a couple on here. All the 11s have to be disregarded because they're the test signal. But if it doesn't end in 011, then it was a coincident rival. And this one never repeated, unfortunately, but it was interesting.
Do you know the guy down in Panama?
Yes, Ben, he's not active any longer. His health and his health of his wife deteriorated, and he gave it up. He actually donated the telescope to the University of Panama, and he gave them my name in case they had some. I made a lot of it, but I never had any contact with him.
So I worked with him a few times because he had a Servo 2, I believe. And I looked at a picture of his mount and I thought it was an alt mount. And no, it's just he lives near the equator.
No.
Yeah, I think he's 7 or 8 degrees north.
Yeah.
So it was kind of an unusual telescope. When I first met him, it had a friction drive with wood discs on it, and it wasn't getting particularly good results, especially with the humidity down there. So we built him a new friction drive with aluminum wheels and a much better way to put pressure on the wheel, and we changed it to your controllers and stuff. And it was getting pretty good results at the end. It didn't have any encoders, so there was a limit to how close it was going to get. It was everything he needed. I was really sorry to see that. Yeah.
I had another question. You've obviously written a lot of software. I was wondering what language you use.
Most of that is either Visual C or Visual Basic.
Okay.
The reason, none of that stuff is fast enough for real-time control, but what it does mostly is over in the electronic boxes, there's these data acquisition modules, and the actual work is done inside those modules. So this doesn't have to, I mean, there's no interrupts in this Windows 10 system. So it can't really do any kind of precise control of anything. But like your system, that's done somewhere else, and this software is just the interface to it.
Right.
Question? Okay, that's sort of a general question.
It's very hard to see.
So, is your searching weather related or clear sky related, or I mean, are you searching all the time?
No, I don't have to have super good seeing or anything because it works on the principal ray, and the focus isn't even very important as long as all the energy ends up on the photocathode of the tubes. I don't need to have a razor sharp image, so it's not anywhere near as weather dependent as like when you going to do the deep sky imaging and you want the scene to be a couple of arc seconds or better. I live in the Santa Fe, New Mexico area. We have good skies. The scene's not always great, but the visibility is good. Right, this time of the year, it's pretty much clear all the time. But the scene is not always good. I would say it was 5 arc seconds or so. It's not super good.
So when are we going to see the CNN news? Astronomer finds intelligent life beyond our galaxy.
Well, it's a long shot thing with a big, huge payoff.
Yeah.
I've been working on it for like 10 years now or so. Each time when I get one generation of camera done, then I start thinking about the next, kind of like what I guess Mel does with his mirrors.
So is your instruments, on all the time, like trying to detect?
No, no, it's not remote controlled. The dome's out in the backyard. So I'm in the dome when it's running. I run one star for 10 minutes. At the beginning of an evening, I look and I see write down 5 or 6 stars in one area of the sky. And then I just go from one to the next and let it scan for 10 minutes and move to the next and scan it for 10 minutes. So no, it's not out there running all the time. It runs only when I'm in there.
It doesn't work in the daytime. It has to have dark and minimal cloud. It's optical.
Okay.
Yeah.
When it's dark and when he's running.
Yes.
Any plans to turn it into a robotic scope?
No, not right now. I want to get this motor project done, and then I've been working on a new piece of equipment to look for the polarization vector of starlight, and I'm working on that. So no, not really. It's right out in the backyard, and I'd rather be sitting in there when it's running anyway, in case something goes wrong. It runs pretty well now. I've got a lot of the bugs worked out of it. I usually go through the whole night without having to do anything. Early on, of course, there was some issues, but it runs really smooth now. All the equipment is homemade, basically, except for the CCD camera.
What's your polarization unit based on?
It has, unfortunately, the picture is very small, but it's shown on the back of one of these pictures here. I'll find it. This one here. This one here, it has two boxes to it. This one has a photomultiplier tube and a power supply, and then this one has rotating polarization filters. So if the starlight was polarized, it rotates in at 90 degrees and it scans and then looks for the diminishment of light from that polarized beam. And then in that same filter wheel that I showed somewhere here, I have one wheel that's for the my general search with the neutral density filter. And then I have another one with some passband filters for common laser frequencies. And I can rotate that in and see if there's a signal that's polarized or not. It's in development, but it's a long way from being where I want it to be. That's what I'm working on right now, in addition to these motors. The motors, they look easy to build, but my experience was that they weren't. The coils took quite a bit of time to get them to look the way I wanted them to.
Okay. Any more questions? Any questions, Zoomies out there? No? All right. Thank you, Bruce.
Yep, thank you. Thank you for listening.
Thank you. So let's see here. We'll stop the screen share. And I see Russ is here. So a suggestion for rejuggling our schedule. If you're ready to go, Russ, would you go? Okay, so let's go ahead and put you on, and then Joe can go after lunch, and then we'll just continue on with the rest of the schedule.
Yeah,
So,
and I won't take too long. Mine's not a real long briefing.
Okay, so you should be able to
Okay,
share your screen at any time.
Okay. Again, does that show up okay?
Yes, it does.
Okay. So the first thing I want to do is so we moved from California to Arizona a couple years ago, and I built we moved to be with Cheryl's daughter, and so in one end of her daughter's house, we built a granny quarters and added a little kitchenette and a little bathroom and an out back door patio and sliding door. And in the backyard, of course, there's an observatory. And so it's not very large. It's about 8 foot square, and it has a tilt-off roof, so you can kind of see the roof slanting there, and it's counterweighted. and not in this picture added, since this picture is a linear jack screw that opens and closes the roof. And so that's pretty convenient. The when I first brought it there, it was worm gears. That's what I was using in California. But Dan very kindly built a
No, you're breaking enough. We didn't hear the last
there
couple of
and the
sentences.
shot. Okay, is that better?
Yes.
Okay, let me move the computer over here. The yeah, so yeah, Dan built the coils and the motor and so forth. When we first tried it out, it worked real good in RA, but it would you couldn't turn the gain up very far in the deck. And so the deck shaft was hollow tubing and a fairly thin wall. It was steel, but so we decided to replace it with a solid shaft. And Dan, as I remember, the you and Dave had a bet whether it would work or not. At any rate, it worked, and so
Dave owes me a beer.
That's right. You bet a beer. And the main use for this telescope is going to be for, it could do speckle interferometry, but I like to use larger apertures for speckle interferometry because we can get closer binaries with shorter time periods. So the main use of this telescope is going to be for a time series photometry. Primarily, Gaia has discovered a whole bunch of new eclipsing binaries, thousands of them, and their coverage typically for the DR3 release is kind of like between 80 and 200 or so observations, just randomly spaced in time. And so if it's a very more than 2 or 3 days, it means that the eclipse itself may just have 3 or 4 points. And so the idea of to use this telescope for follow-up is to, you know when the eclipse is going to be fairly closely. And so then we'll just fill it in solid with points in at least 2 colors. So the filter wheel's automated, and we use Dan's SciTech software. Works just really great. Very happy with it. And at any rate, so that's all set up and planned to get going this coming spring. I'm leaving for Hawaii for the winter in about another month here, and we've been working on the, well, I'll show you that next. So that's one project. And then the next project is I'm teaching astronomy research at a local community college. So Rachel Freed is on the faculty here and remotely, and she teaches the introductory astronomy research. So they just do CCD, just CCD regular imaging of somewhat wide binaries. And I do speckle interferometry. But at any rate, and so we wanted to have our own telescope. The original idea was to get a telescope and put it either at Sierra Remote Observatory by Yosemite or down at the El Sas Observatory in Chile. And but when I even hinted that we might consider putting it on campus, the local powers that be, they went wild and says, "Oh, you got to have access to it," and the people in the town wanted to have an observatory. But anyway, to make a long story short, I decided, we'll we'll put it on campus. We knew it would be lots of work, but so where we're at is the Karas Foundation funded a 0.5 meter plane wave instrument telescope, completely instrumented. We've got a nice QHY 600 camera behind a straight through it, and we got a Botter 3-port instrument selector, and so straight through goes essentially a wide field camera with a filter wheel, and then one of the other 2 ports goes off to the side to a Barlow and a camera and filter wheel for speckle interferometry and planetary imaging, that sort of thing, narrow field, high speed sort of things. And then on the other side, it goes out to a spectrograph, the ALPI spectrograph. So it's low resolution, but it's the one spectrograph that's been successfully automated by a number of folks. And so anyway, so that's the telescope. Was ordered, maybe 8-9 months ago, and it's would have been delivered, I think, a few weeks ago, but Plane Wave Instruments having a little problem with the glue holding their mirrors to the telescope. So anyway, they'll get it solved and it'll show up. And then we've we've put together a proposal for a 16-foot ash dome and total automation, all the weather sensors, scene monitor, the whole 9 yards. So the first proposal for the telescope, it was $128,000, and then the proposal for the dome and so forth, it was $270,000. So it's quite a bit of money to have this all done. We have an expert from Tucson that has a company that they're in telescope automation. And anyway, this picture here is a picture of the 0.5 meter plane wave instrument telescope, not at our place yet because we don't have the dome, and the 16-foot ash dome, and it's at the King's Academy in Jordan. So this is a telescope in Jordan. Hopefully they aren't getting hit by rockets. But any rate, it's a lot like ours, except and ours is on an equatorial wedge like this one is, but this one doesn't have much in the way of instruments. Ours is more completely instrumented. Okay, so this is kind of what our dome will look like. It's actually on the campus up on a little hill, and it's going to have a platform surrounding it with a little wall so people won't fall off. And we can set other telescopes and like a small solar telescope, so forth, out on this kind of wide ramp that goes around it. So that's kind of the second project that I've been working on, is for the college. The third project is we have there's a bunch. This is El Sos Observatory. It's out in the Atacama Desert. It's really close to CTIO and the 4.1 meter SWORD telescope, almost within seeing distance. And under one of these roll-off roofs is a CDK 1 meter telescope. And so we've had time. We're starting our second year, but we have a full year of observations starting last October. And yeah, can you still hear okay?
Yes.
Oh, okay, good. So starting last October, every month we got a number of nights, full moon. People didn't want near the full moon, but speckle works just fine, full moon or not. And so we've gathered speckle interferometry on hundreds of known binaries, most of them quite close, kind of ranging from around 0.1 arc seconds to 0.5 or 0.6. So they're mainly ones that are closer than Gaia can handle. Gaia doesn't do well once it gets below around 0.6 of an arc second separation. It doesn't see them as two separate stars. They're pixels too large in the resolution. The telescope isn't very large aperture. And so there was lots of data, about 4 terabytes of data, raw data, and it got uploaded as it was taken to Google. It turns out it's very hard to get 4 terabytes off of a Google Drive in Chile. That actually took months. And so they finally got it downloaded. We're renaming the files to get them so we access. So anyway, lots of work to make that data, and we're starting to gather our second year. Some of these systems, they're really short, just a few year period, and they'll be sizable movements from one year to the next. And finally, the other program that I've been working on, and so, oops, sorry about the, there we go. Anyway, the other program is observations of Mount Wilson. So we've been going every summer in June to Mount Wilson right after the SAS meeting for several years. And so there's me, there's Tom Smith, that's Rachel Freed there. This is Paul McCudden. So Paul's been working very closely with us. He's chair of the science department at Colorado Mountain College and is really into speckle and double stars. And our students meet with his students once a week, and students in India. The folks from India they couldn't get their visas in time to make the Mount Wilson. And then, but at the end of the table, this is Leon. He's from Germany. He was a student of Calais at high school, and he's now in college. And he does lots of the programming and stuff for the 1 meter telescope in Chile. And then this is Nick Hardy, and Nick's from Belgium, and he wrote the Nina app, add-on that goes to Nina that does that automated speckle interferometry. So it's the first time it's really been successfully automated, and thanks to software by Nick. He's written other applications for Nina, including their exoplanet application. At any rate, so that's, and Mount Wilson, we had 3, San Diego had 1 night, and we had 3 nights. The first night, normal teething problems, so we didn't get much observed the first night. The second night was better, but we realized we were spending lots of time rotating the dome back and forth. And just on 60-inch, the 60-inch dome isn't very speedy. And so the third night, what we did is we expanded the target list. So the known binaries would usually pop up and be within the slit. So we wouldn't have to move the slit, or if they weren't quite in the slit, we wouldn't have to move the slit very far. And so at any rate, we observed 50 binaries, known binaries, and the data got downloaded lots faster, and Paul McCudden got the files sorted out, and we've automated the first part of the reduction from the big files to what's called the BSP files. But at any rate, it does all the fast Fourier transforms so far then, and it reduces the size of the files by about factor between 500 and 1,000. So then they're easy to handle. And so I've reduced by hand all the 50 observations and been studying them. And I did it first manually literally with a protractor and a ruler on the printouts from the Naval Observatory showing the orbits. But recently what I've been working on is using Desmos. I don't know if any of you know that, but Desmos is it's an online graphing calculator. So it's kind of like the old HP calculators on steroids, and it's really really nice. And so this is a one of the ones we observed. And if you, I don't know if can you see my cursor, or does that not show?
Yeah, we can see it.
Howard, can you see my cursor?
Yes, we
Okay.
can see it really well.
So all these. Oh, okay, good. So all these green ones are the green plus signs are visual observations, and then the bright blue ones, these are speckle observations. And then the U.S. Naval Observatory plots, they don't have the most additional. So there was 2 more by Tokovinen on the 4.1 meter telescope. And this is our Mount Wilson Observatory observation from 2023. And anyway, and then I made a new orbit that goes more carefully through these points. You can see this is clearly going off orbit. So the orbits could be wider, the period's a little bit longer, that sort of thing. And so here's the new orbit that I came in. And so this is just showing it going through. This is Tokovinen. Yeah, come on in. Oh, thank you. Yeah, appreciate it. And it goes through, and these Tokovinen observations, they're like this one here is off less than a milli arc second. Less, I mean, they are, Tokovinen he's superb. They were just super accurate. Our observation was off about 7 milli arc seconds. So I mean, it is really close. Of course, we were just using a 1.5 meter telescope, and these were 4.1 meter telescope. At any rate, so that's what I've been up to. And it's keeping me busy. I'm giving also doing a flying aviation thing. I've kept up instrument current, so that 83 still flying instrument approaches, and then I'm part owner of an airplane, and we're working with the city of Payson to expand the airport facilities and facilities at the college. So I was actually got hung up today working on a presentation for the city council as soon as I get back. So I'm sorry I missed some of the earlier talks. I did catch Dan, I caught the end of your talk. Anyway, that's it. I'd be glad to answer any questions.
Okay. No?
Go for it.
All right. No question. Well, it's really good to see you, Russ, first of all.
Yeah.
Yeah, you had me a little worried when you weren't weren't available first thing at 9:30. So yeah, it's real good to see you. And for those who don't know, Russ he started this workshop. And without him pulling us together, God, it seems like 100 years ago now, Russ. It's been a long time.
Yeah, it's 14 or 15, something like that. Yeah.
Yeah. And so, without Russ getting this going, we wouldn't be here today. So he found a real sweet spot, I think, in terms of a cross section of professional and amateur telescope making. And, we've just kind of run with it since then. So as always, thank you again, Russ.
Yeah, most welcome. And I think it's good to point out, I think the Altas initiative was quite responsible in many ways for the plane wave direct drive telescopes and their success with the CDK 700 and the 1 meter telescopes that's spreading around the planet. So 3 cheers for the Altas initiative. And thanks, Howard, for keeping it going.
Oh, my pleasure. My pleasure. We have a question for you.
appreciate your supporting all these projects and everything, but I wonder if in the back of your mind, there's the next impossible dream.
Yeah, well, I organized several American Astronomical Society workshops on small space telescopes. And so and we actually had a little workshop, if you remember, Howard, back, what, 5 years ago. Remember, a couple of the my Cal Poly students came up. And
Oh yeah, I remember.
So that's kind of an impossible dream. And I guess another dream, one that I'm working on is I'm trying to work with other community colleges, rural community colleges that don't have, so we can do shared facilities and have shared classes. The students are widely dispersed, so you have to get the classes across a bunch of colleges in order to get a decent class in a specialty like astronomy research, and also that we can share facilities. So that idea of that half-meter telescope that I showed you earlier is not so much just for our college to use it, but for it to be shared with the other rural community colleges in Arizona and the Southwest. So that's kind of my two dreams. Plus taking it easy in Hawaii on the beach.
Yeah, that's always a good dream. Yeah.
Thanks, Russ.
Yeah, thank you so much.
Yeah. Thank you, Dan, for hosting it again. That's great. Yay.
It's in our new shop now, we had to move.
Ta-da.
Did you hear that?
Yeah.
Me and them.
Okay.
The last time we were here, we were on Cutter Circle. You remember that, you've been there several times, but we had to move our whole shop. So we're in the same neighborhood, but we've moved.
He really means it.
Yeah, it's not far.
Like you can imagine.
You hop, skip, and a jump away. So we're gonna turn this over now to Joe LaCour, who's going to give us a LIGO A+ upgrade. But let's see, you want to do the first part without being recorded?
Yeah, you keep it.
Okay, so I'm going to stop the recording briefly. So we can do this part.
First slide up real quick.
All right, let's see. Yeah, the first slide.
It's just a little funny story that I might not want the world to know.
Okay, so this is the first slide.
Just don't want to record it.
Just remind you to start the recording.
So LIGO.
Okay, hold on. This is
slide.
This isn't. I need to screen share this, I think.
Yeah, you can do that.
Yeah, before we can get going here. So
I've been working with but anyway, LIGO Observatory in the I guess you can call it the assembly lab, where only the scientists and engineers can go, in the bathroom, in a stainless steel box with a key, is the cheapest toilet paper you can imagine. There's the picture of it.
Good for them.
Okay, and my son just happens to have a lock picking kit for some reason, so he opened it, took a picture.
Yeah.
Next picture.
All right, hold on.
And in the visitor center.
Okay, let me stop let me stop the recording.
Well, you weren't. It's not that critical. Just don't put it on YouTube. That first part.
It's.
Way up at your upper left corner where it says recording, and there's a pause button.
Pause button.
Pause button for.
There we go.
So
Okay,
anyway,
all right.
The next picture.
Okay, so let me share the screen here. Okay, share screen.
It was cheap. It was bad. Locked up in a stainless steel box, right?
All right, so let me share the screen. Okay, so there's the toilet paper.
It's up in the visitor center where the public has access. Is the Nobel Prize under some acrylic? So there you go. Isn't that something?
Who's Nobel Prize?
Ray Weiss. So he got one, and Kip Thorne and Barry Barish, I think.
Mhm.
But Ray bought 2 extras for each observatory in Livingston and Hanford. So anyway, all right, go ahead. You can share and record or whatever. But anyway, and that's moved now. They got a new visitor center in Hanford. If anybody goes, it's a new science center. And like maybe that's still in the front office. I don't know, but it was being constructed when we were there. Now, when did we do this work? Was after COVID started in like September, October. So that would have been 2021, I think, or 2020. I don't remember the dates of the.
So when you just click through the
Yeah,
next
that's
one?
fine. That's fine. Yeah, just so there is we were there late one night, like 8 or 9 and 8, and that's LIGO at sunset. Everybody knows where this is?
Hanford, Washington?
Hanford, yeah.
Hanford.
It's out in Hanford, yeah.
This is the other one in Louisiana somewhere?
Right, Livingston, Louisiana. And okay, so here's the beam tube standing on the I think it's the bridge looking out towards the beam tube.
And how long is that?
4K.
4 kilometers.
So there's a vacuum tube about 1 meter diameter, 4K long, in 2 directions at each observatory. And they got the alignment of the optics to hit the target on each side. Yeah.
And it's a really deep vacuum.
Yeah, it's very hard back. So there's in the I guess it's the meeting room. That's the events, and I can't read them all, but there's whenever they have a big event, probably not anymore because they can't have that much champagne, I guess. But those are some of the early detections that were on the shelf. I put them on the table, took a picture. Okay, next one. So that's up on the roof, looking out towards, I think that's looking towards the northeast at the, I can't remember what nuclear plant that is over there. But we got to go up there. So there is, during COVID in the control room, can you take some of that stuff off?
I wish I could.
Lift it, see if you can lift it up.
You
If
know,
you want to see that.
I wish I could just get it to go away.
Wait, can you go help?
It's, wait,
Go about 2/3 of the way down, there's height something.
Hide video panel. Well, that didn't do anything.
Grab it and grab and lift it.
Oh, wait, there we go.
Better.
Okay,
Oh,
there you go.
there we go.
So, oh, you can't see it that well in that picture. We'll get to the next picture. So yeah, that's my son Trent who worked with us. This is actually a picture before COVID, but I put it in because this is you can't see the center,
Sure.
the screen in the center at the top right there.
This one?
Yeah, that's that's what they're reading. And that spike on the left is the 60 hertz spike somewhere.
Right here?
Yeah, I think that's it. Or maybe,
Or maybe there's one here.
I think that's it. I'm not sure. I think I got it on a better picture.
60 hertz is from having power.
Yeah, everything all over. Yeah. And there's noise all over. So go to the next one. Let's see. Okay. I think you can see it. Maybe that's the same picture. Yeah. The same time. Yeah. And it's kind of neat, but on the very left at the bottom or top of your image, on the wall, over there is the I think it's like the calculated binary neutron star distance. So they actually have the distance reading of what they're doing because of the noise level. So when the noise is low, the distance goes up. Kind of a neat little screen. And that's in the control room next. So here are all the drivers who was talking about that? Somebody was for all the actuators.
Hmm.
And all those cables have to go to all over the place. And
So those are actuators for the mirrors.
well, wait, let's start over. Okay, they call them actuators, but Trent says they're space taker uppers. Okay, that's you heard me say that, because what they act like is everybody's held a chicken, right? So you move the chicken and the head stays still. Well, the neck is the actuator. So it just takes up the space. So when the earth moves, it keeps the instrument still.
Ah,
and
cool.
the primary is the hydraulic actuator that's on the ground. The ones that we did on this build, it was only 28, are the internal in vacuum actuators for the next level. So that's a chicken sitting on top of that chicken's head. Okay. And you'll see that in a minute. So those are the drivers.
Excuse me, Joe. When you say we,
Oh,
who is we?
my son and I guess.
Oh, you did the LIGO upgrade.
No, just the actuators. You'll see that in a minute.
Okay.
I was
trying to get
contacted.
context
I'm
for
gonna get that in a
time.
minute. Yeah,
Okay.
I'll get that in a minute. So this is inside looking, I guess the northwest arm or something.
Is this part of
is
the tunnel?
Yeah, this is, wait, this is, no, that's the laser room right there. Yeah,
This okay, this is the laser room. All right.
And I believe, oh, I'm kind of lost here. You don't get in here very much. Or maybe that's I'm not, because Hanford is different than Livingston. I'm more familiar with Livingston, but that's the beam tube going out over there.
Okay.
Yeah.
All right.
That's the beam tube.
So this one.
Oh, we got a pointer. Which button is it? The green button.
Okay.
Why is it not? I don't see a thing.
It disappears on the
It
monitor.
disappears on the monitor.
Oh, really?
It absorbs it.
Okay.
Oh, well. Okay.
Laser doesn't work on the
So
monitor.
this is the beam tube over here on the right,
Heading out. Yeah.
heading out. Okay.
I believe.
Okay.
There's a lot.
Well, you
going on
could say
there.
anything and we would know any
I
different.
just- yeah.
All right, we'll go to the next one.
Okay, so this is the primary hydraulic external isolator, and that's what that actuator is there. And you can see it laying on its side there. There's one vertical and one horizontal. So that's the corner of the 4 points that go into the chamber through bellows to hold the instrument. An instrument package. I don't know which one it is. But
What is that, avoid, oh, never mind, I understand.
yeah, yeah, suspension is HEPI is unlocked. I'm not exactly sure what that means, because they turn it on and off sometimes, and when they do maintenance, it might have just put that there. So, okay, next slide. And there's another picture of them, so you can see how they're on the corner of each one.
Okay.
Okay, so I guess it was about 2020 or 19. I was contacted by the MIT engineer. He says, "Hey, you want to build some actuators?" And I said, "Well, what are they?" And he says, "Well, no problem. We got all the procedure, we got the tooling, because this other company built the 300 or so that are installed now. We just need 28 more for the A+ upgrade for the chamber that they're adding in. I think it's 300 meters away or something." I said, "Sure, why not?" So we got the procedure, we got the tooling, we looked it over, bid on it, got the contract, and then I started really looking into it, and I realized there's some weird stuff going on here. I didn't get it. So is there any way I can contact the engineer from the company that went out of business that made these the first time, designed and made them? So we found him. We have a conversation with him on Zoom, and I'm asking him questions and he's answering, but I got the picture that he didn't build these. It was downstream to a technician, several more layers. So but he knew enough about it, so we talked about it. So the bobbin, the electromagnetic, I want to go get the thing, but so that's the bobbin that the two coils are wound around. It's aluminum bobbin, and the 20 gauge wire, polyimide wire, wound in two directions. And the procedure said to do a high pot test after it's baked. And I noticed that they were baking it to the polyimide bake temperature of 300 C, but the wire is only good to 250. So that was the first clue that something might not be right. So I'm talking to him about this and asking him questions. And I said, hey, did you ever have any failed high pot test? And he says, we had 100% failure rate for 2 months. So like, I was just, wow, this is bad.
I doubt if very many people know what a high pot does.
Oh, it's a high voltage breakdown test of the insulation.
Put a high voltage on it.
High voltage on it.
And if it leaks, then it's a failure.
And it also really messes it up. Yeah. So anyway, so that's the actuator. So it actuates in this vertical direction. I can't do it. And it's only a very small amount, microns. There's magnets on the inside, and we'll get to that in a minute. So go to the next picture. Let's see what that is. So there's a side view of it that's installed that I think I found that on the internet from LIGO. That's one that this previous company made that was installed. Okay, go to the next one. So there it is on the, see it right there. Yeah, that's one, that's an actuator installed in on the platform. And I believe I can't remember which side is the earth and which one is not the earth. It's the top of that. And the other one goes to the platform. I can't remember. So, okay, going to the next one. So this is there's 1, 2, 3, and then now is the fourth thing of the suspension. So those are springs up at the top, like fishing poles. The triangular pizza slices, that's a spring to support it all. The rods that go down are lets it traverse. And then you've got another set, and then it goes to a the third pendulum. It's the easiest thing to say. And then that's the test mass at the bottom left, and the reaction mass is at the right. And I don't really understand all this. I'll be honest with you, it's very complicated.
Masses down at the bottom are actually optics, right?
Right. I think the reaction mass is the intermediate one. I don't.
The mirror end of the leg of
Yeah.
the interferometer, right?
There, yeah, that is a piece of fused silica.
Yeah, yeah.
And I think it's about it used to be 10 inches, but I think they've increased it to like 16 or something, but it's a metric number. And they're hung on quartz fibers that are really small. I don't know how they did it.
0.4 millimeter.
I saw a video by Jason Kendall on this
Yeah.
and he explained it and how you can use some.
You can do a little demonstration.
Yeah,
Yeah.
with strings, yeah.
It really is something.
It's amazing.
But they hang them on glass fibers, and then they transport them and put them in place. But the glass fibers are not loaded, but then they gotta release it, and they have had them break, and they just get another one going. But it's the only way it could work because of the quietness of the quartz opposed to steel, which was the original. So go ahead to the next one. So, and there is, I believe that is the actual one.
Wow.
You're looking at some money there too. Yeah.
Wow, that is some fancy
it really is.
technology.
I've never seen that. I've seen the example that's in the showroom over there, the visitor center.
So this is between the guillotine valve. So
think
taking the services.
This is probably the intermediate test mass, but yeah, it's in between valves, so they can get in there.
Yeah,
because they can close off the beam tube.
Yeah, they can close off the beam tube with a guillotine valve, and then they can vent this and go
Crawl,
inside,
yeah,
and then pump it back down and open up the go.
Right. I know. I know. Well, they have roof blowers that they start with, and then the final thing, they've got a cryo pump going all the time. So go to the next one. Okay, so here we go. So LIGO had a failed actuator bobbin. So I get it. There it is. It's got resistance to the coil. So the coil to the bobbin. So the original specifications wanted the bobbin to be machined, anodized, the non-surfaces that didn't touch the copper machined off for insulation. Well, LIGO also has a rule that says no anodized aluminum anywhere in the vacuum system, no matter what, unless approved. Well, I just said, look, I don't want to do that. So I got a better idea. So based on how hard it was to scrape off the polyimide off the failed bobbin, I said, I want to paint the surface with polyimide, bake it, and then wind on top of it. And they're like, well, okay, that sounds, we'll try one, you know? So that's what we did. And it worked perfect. And that way the bobbins were not anodized, because anodized is porous. That's how they dye it. And they don't want it in the vacuum. So I said, hey, they're like, well, if you can not put it in the vacuum system, that's great. So here we are. So it's got resistance. So I'm lazy. I don't like to do work one time, let alone two, right? So here we go. So what do? You hook it up to the meter and go ahead and you start unwinding until it went open. And then I found the spot. I could see it. It was one of the holes on the edge had a burr, a little burr that didn't get deburred, and the wire that was touching it, when it got baked, it shorted it and smushed the polyimide down and probably had enough resistance. So here I am checking it in salt water so I can find the exact spot and look at the wire under the microscope and see exactly what happened. Wow. So I call this draining Loch Ness. I mean, you just figure it out, because I don't want to do this again, because now you got to, if it failed, you got to strip the bobbin and start over. And that's what this other company did. They said they had drums of copper because they didn't go figure this out. They just kept whining until they got enough to meet the contract, and that's it. So there could be some at LIGO right now. They're really close to the edge that just passed the high voltage test. Another volt could have, you know, broke it down. But anyway, so
did you de-blast these before you wound them?
no, you'll see that in a minute.
No, what is baking?
Hmm?
What is baking?
Oh, the polyimide is, oh, you'll see the bottle of it. It's used in semiconductor stuff for insulation, and it's a
Heat cure, right?
yeah, it's like a heat cure varnishy looking stuff.
And it's got volatiles, and the vacuum here is like better than space.
Right. So they want to get it
Literally.
really.
It's, I forget what it is. It's like 10 to the minus 12.
Oh, I don't think it's that high, but it's getting up there. It's certainly 9.
It's certainly 9.
Yeah.
It's at least 10.
So the baking just gets all the volatiles out.
Yeah, and it hardens it, and
Hardens
it's
it,
hard.
yeah.
It is like porcelain. So here's me in my little shop trying to figure out what's wrong with these two failed bobbins.
That's a
So
nice flower there on the middle of the screen.
yeah. So anyway, we're talking to this engineer. So we call him back, and we're getting on the phone with this engineer that was part of the company that built 300 of them. And I told him, I said, look, I think we figured it out what happened. I've explained everything. So here we are. My shop is attached to my house. My son is listening to me. We're on speakerphone. He's sitting there, and I'm in my living room. You know, kitchen's right there, couch is right there, computer desk. And the guy says, wow, you figured that out. You must have a better lab than we did. And it wasn't the lab. It was being lazy. I don't want to do this again. So
Okay, that's awesome.
so anyway, so here is the cross section of the magnet. Now, the coil and the magnets. Now, somebody can help me out on this, because it's opposing coils. So when you energize it, it goes the other way. So it makes 2 poles the same pole to the middle and to the outside. Okay. And but you're getting up to help me there. I'm on the way. Okay.
I can't see through your body.
So the best thing we can understand is it was based off of a voice coil from a company called can't remember, West Coast company. And you wind them in two directions to cancel inductance. Okay, so you can operate at a faster, higher frequency. You got that. But
Closely coupled coils.
yes. So when you push it, it makes two norths. Well, you know what I mean. It makes two norths in the middle. In the black line, it's going to squirt out a pole. Let's say it's a north, and it's going to see these magnets on the side that are this way. So it's going to make it go away from that north and towards the south. But what happens to the other pole that goes? It's going to be in the metal. Oh, the black hash lines are steel, and it goes around to that north. It's still, I still can't get it in my head how this thing works.
It sounds like it's self-compensating, so if as you deflect, it wants to go back the other way.
Well,
Is that the idea?
I don't know. No, it's just to not have any very precise. Now these are not used much because they don't want to put any DC in it because now you're putting energy into the vacuum. They might use a little bit, but they try to take the DC out with the external stuff that's hydraulic. But anyway, this could go, it actuates in this direction and that direction.
Yeah.
And the dots are the wires. The pink is the aluminum. The yellow are the magnets. And that's the way it works. So
It looks like it flex it in like this.
no, it shouldn't go in. It only goes
Is the idea to actively compensate for
any vibration.
vibration?
Yeah.
So
So you got a big old stack of chickens
Yeah.
on each other's
I
head.
know, right? And
Right,
you
it's what it
mentioned
wants.
chicken head. So
Yeah.
I'm imagining what this thing does is with the opposing magnetic fields and the way that's configured is that if it gets too far off one side or the other,
Well, it's closed loop. So you got a geophone on the ground, and then a geophone on the top of that hydraulic,
okay, so
and then a geophone
so there's a feedback loop.
feedback. It's
and
all
the
closed loop.
feedback loop tells us which way to move,
Right,
and it moves.
and it moves fast.
Okay, got
So
it.
is that right?
You know what? This is a little over
You
my
look
head
like
too.
you.
But I had a question. So what CAD system did you use for that?
Oh, that was on a piece of cardboard really quick, and it looked okay, so I went with it. Okay, so here we go. I think the next is we're gonna start making actuators. Oh no, that's another picture of it. So the translation is from the southeast to the northwest in that image. And that's the magnets too. So here we are in the shop making bobbins. Now that is a big part from my shop, but it's aluminum, so we could do it in the CNC machine. So because it's thin wall, we did a lot of roughing and then started. And oh, there's just the bobbin sitting up there, but just for reference and stuff. So go ahead to the next one. There's a bobbin in the clean room at LIGO. And that's Trent. And so the original contract that LIGO wanted was all the parts get made, including the magnets and the wire, shipped to LIGO, get clean, return to the vendor to use in their clean room, to assemble them in the clean room. Wow, clean room. I don't want to build one. So I said, how about you just leave them at LIGO and we'll come over and use the facility to build the actuator. Right? I mean, that's pretty easy, right? So they all thought that was okay. You know, it worked just fine. So we get there and of course we want to wrap it. And the first thing Trent says, he says, wow, somebody knew what they were doing because he programmed all the parts on the CNC machine. and I did most of the running, but there you go. And it was hot. This was when the place was burning over there. So when was that, all the fires?
Yeah.
It was before the vaccine, which would have been like
I think it's 2020.
2020, like September of 2020 is when
Yeah.
this was. So the procedure said, paint the polyimide on, wind a layer, paint some more on, wind a layer. And I talked this over with another customer of mine, technician at another customer, about winding coils because he had done a lot. And he says, you're going to make the biggest mess. And I said, well, that's what I got to try, you know? So Next slide. So there's the polyamide. That's $850 worth of polyamide, and we used about that much of it, like hardly any. Okay, and it's I think it's still in a freezer at LIGO. It's got to be kept in a freezer. Okay, go ahead. So there's painting it on and baking it. That's not baked yet. No, that is baked, I think. And so that's in the class 1000 clean room. Anybody notice anything interesting there in the class 1000 clean room?
The brush?
Yeah, the brush. They've said to use an acid brush, it wouldn't work. So I just brought some artist paint brushes and I said, we're going to just use it. Be careful. And every now and then a hair would come off. You could see it, just pulled it out. So it worked great because it could paint that on there and bake it. And that's better than anodizing. So, okay, there you next one. So there's the mess. Isn't that beautiful? It just runs out. And we put that in a test cell to test it, the first one, just to verify. It made a mess. So I went and scraped all that off and we re-cleaned it. And I think that's actually in service. So my customer that told me that's going to be making a mess, he says, take a clean room lint-free cloth and saturate it with the polyamide and let the wire run through it. And that's what we did. And it worked just great. So go to the next one. So here we are. So the wire had to be unspooled, clean at LIGO. That's Hugh. That's Hugh. That's the engineer at LIGO on the left. That's Trent. And unspooled. And I ordered just enough wire with a little bit left over because what could go wrong? Well, that was before we found out about all the failures. So that's winding. Now they originally had a motor drive on the previous company, but we tried it with the lathe, and you'll see why in the video, but we just couldn't see that this was going to work out very well for us. Okay, so that's in the clean room. And remember, this is during COVID, before vaccines, and we were really careful. We all agreed we weren't going to go out and, partying or anything previous to this, because Hugh and Trent and then not. So go ahead to the next one. So when you're winding this is in the wind. Oh, there's the baked polyamide color. You see how it layers this way and then it flips over. It winds, right?
Left hand coil and a right hand coil.
Well, no, it's the same direction.
Yeah.
But it feeds this way, then it feeds this way. So the problem was we got to try to target the same amount on each side. And I think the number was, it was 220 wraps on each side. We never could get to 220. Just couldn't do it. We did a few 215s, 216s, and we talked to them about that. It was a small percentage of the wines, but I think we talked about it being more important for them to match on each side. So, but this is where you end up with, now you got to figure out, okay, do I go one more? Do I jam it in the corner? Because one of the bobbins failed because it jammed into the corner and then baked and shorted. That would have had two failed bobbins. Okay, so go ahead. Okay, so got a wire straightener. Found that on eBay. Some guy makes them in somewhere. And we use that not only to straighten the wire, to put tension on it, so you didn't have to hold it so tight to wind it. It put just a little bit of tension on it. And there's the, can't see the crank. I think it's better in the next picture. Go ahead.
Maybe it's over here.
Yeah. So there's the crank and a counter. So here's Trent winding a coil. We did each about the same amount because it was just hard. You had to just concentrate. And the reason I didn't like the motor drive is it's constant speed with the foot control. But this, you want to stop, you want to put it in the right spot, you want to go a half a turn and put it in the right spot. So you'll see the video of it. Head to the next one.
Okay, so there's a counter right here.
Yeah, no, that's not the video. So there we are winding a bobbin. And also, you got to play a little, do a little forecasting, because you want to not end up at a number in the middle. You want to make sure it gets to the end before you flip it around and take the bobbin off and flip it and go the other way. So I think you go to the next one. Let's see. So there's another picture of it. That one's about full. I think that is full. 208. Right? Yeah.
Yeah.
So we would hold it, unscrew it, flip it around, and reverse the winding direction, making sure we did everything just right, because that way we're always going in the same direction. And it just worked. It worked quite nice. Yeah. So go to the next one. Oh, here's the video. So this is about how fast you went right here. You laid it in, you looked, and sometimes we'd have to stop and look at it and say, should we go one more, or should we start going back right now? I mean, it was that, it was that, because you look at the counter and say, well, I need to get one more, but I don't have it. What do we do? Well, we just deal with it.
So how long would it take to do
One?
one?
A couple of hours.
Yeah.
Like 2 or 3 hours. Yeah. Something like that. We got better at it.
Sure.
You know?
Sure.
But we did 30. We had 30. They wanted 28, but I made an extra 2 bobbins, and they said, we want them, wind them. So, we're on the phone with them during this stuff. So, but this, you may learn something about winding the coils for the direct drive too. That's another reason I thought it'd be good to do this, to show this presentation. But can you see he's got a little, you can't really see it that well, but there's a little rag, or maybe that was the first one with the paint on, because I don't see it. Maybe in another picture. Go to the next one, let's see. What there was oh, he's definitely got it there, the rag. The towel with the impregnated paint. So we paint on a little bit, wind a little while, and paint it on the towel and running the wire through it. So it's just a thin coating on it. Okay. And when you bake it, it doesn't drain out all over.
So the wire, you buy the copper wire bare.
No, it's got polyamide on it. Baked. Oh, and that was another thing.
Well, to glue the wires together, solid piece, so that they don't vibrate.
Right.
When you start passing current.
Or move, yeah. And stay below the surface. So the manufacturer uses a wax on the wire. And of course, they found this out, and LIGO says we got to clean that off. So they had to unspool them, and there's some spools down there of leftover, I believe, but all on the rack behind him in the foil are the cleaned lengths of wire that we estimated that we would need plus 5%. So it had to be cleaned, the wax had to be cleaned off. And we found out later that the company that was having problems just gave up and just started winding it off the spool. And LIGO didn't know that. So
that was their 100% failure.
The deburring, we think it's mainly the anodize is not that good, and the burrs on the inside, because they had holes that went into the trough where the wire was, they weren't deburred that well, and they tried to jam in the wire to meet the number of winds, pull it really tight. We think those were the main failure modes. So
Are you saying there's a bunch of wax hidden in there?
no, not now. No, there could have been, not a bunch. In fact, it was probably hardly any, but it was just not a clean. They said we can run you a bunch of clean wire, but you're going to buy a pallet of it. So because they got to clean the machine and then run the wire through the processing. And you see, we even had a block of wood in there under the aluminum foil. There's a block of wood for a hammer.
Under here?
Yeah, that shouldn't be in there, but we made a decision to do it because we didn't have a choice to go get any other thing to do that with. But it was all wrapped up in aluminum and screwed down from the bottom, so it was fine. Next thing. Okay, so there's the wire going through. Of course, I think he's got one sitting on the ground. Is it sitting down? Or maybe he's just, don't know. I don't know why oh, we had to put it in aluminum because the chemical, which I can't remember what it was, started going through the glove. And it made his fingers wrinkly. And mine too. So we just wrapped the little towel in aluminum. I don't know why he set it down. He's probably adjusting something. But that's winding the coils. Okay. And it was hot in there too.
So can you pause partway through doing this, or do you just have to keep going till when it's done?
We can wait a little bit, but we want to get it finished to put it aside and get ready to bake. Well, there's more to this. Okay. So yeah, we couldn't wait for the next day. Like once you start one, you really need to finish it.
Yeah. Okay.
So there's a 207. And so I had to dream up all these little clamps to hold it down the most effective way. So you see how it bulges up in the middle a little bit? That had to be flush with the surface or below. And the original manufacturer had these clamps with these big Teflon blocks, and we just couldn't see it. So we did something different. We had strips of Teflon that we screwed to a plate to clamp it down. And that didn't work because pushing it down, the wire wants to squirt out the side, trying to clamp it. They had too tight of a bend there that should have almost been an ellipse, feeding the wire gradually into the flat. That would have helped. And maybe not trying to pack so much wire in the thing, because the engineer probably took a cross section and filled it with dots and said, oh, sure, it'll all fit. Well, it doesn't work like that when you're winding. So what we did was, on the fly, we quit pushing it down. And actually Trent thought of this. He said, let's slide it on like a sled. So we hooked the Teflon strips to the aluminum plate and put it on the edge and pushed and slid it over, but it was still really hard. And you'll see the next picture. I think it's the next one. No. Anyway, that's a completed bobbin, and the wires all look good. Yeah. Okay, go to the next one. Oh, there's a polyimide painted, baked, ready to go. So it just took an extra step because it had to be painted, baked, and then the next day wound on. Okay, next one. Okay, that's me painting or doing something, setting something up. Oh, it's probably, that's the little slide to clamp the wires down, to smash it. When you'll see that in a second. Yeah, there's some. So look at that nice looking lamp in the clean room, huh? Well, we needed something, so we found something and give it a little wipe down. And that's a fume extractor, because the chemical, it was not a safe chemical, but you could hardly smell it. It just wasn't that strong. So the next one.
Instead of aluminum, they didn't use Teflon for the bobbin.
Movement, probably.
Maybe.
Yeah. So here we are, smashing this thing down with my arm, trying to put screws in to hold it flat before it goes into the oven to bake. It was really hard. And one of them, we just couldn't get it. So we put some aluminum foil on the ground and aluminum foil on top, and I stood on it to get it to smash down. So in the lessons learned report after this, I said, if you ever want to do this again, call me to design it, because a few little changes would have made a big difference in just making it easier and more safe to build. So, and there's Hugh, that's Trent, and Nick, yeah.
All that pressure and squeezing the wires together, you weren't worried about
Yes.
squeezing poly in it, of course.
Yes, we were.
Okay.
But on machining the bobbin, when we found out that the burr on the inside, because they anodized it, the original designer builder anodized it and then machined it, they actually put the holes in and they didn't deburr very well. So our last operation on the CNC machine was with a big, like a big key cutter. I say big in my shop is that big around. And made the pass around it, so there was no burr sticking out. So that was the last one. And of course, we inspected it because we didn't want any sharp edges. And in the lessons learned, I said, don't put the holes through. Do blind holes. Well, you can't, you gotta watch blind holes because now you gotta vent the fastener. Maybe you could put a small hole, but you don't want any sharp edges, and you don't want any polyimide flowing up into the threads of the screw holes, which you might have seen on the bobbin. It was designed and built. It wasn't designed and tried and designed and tried and designed and tried and then finalized. The original design of this thing
Wasn't designed for manufacture.
yeah, and that's where I can being lazy and not wanting to do work once, let alone twice. I can think all that through pretty good. So there we are. So there's the clamps. You can kind of see it. That's the clamps, and you see the little Teflon pad flip. Yeah, the little Teflon piece of tape. And the reason I wanted to use tape rather than a block is because you could see that when they had their blocks on it, because I got the old tooling, it's stuck. So I'm thinking we'll just use some Teflon strips that I cut up, with a razor blade and a ruler. So you could peel it off and you wouldn't try to lift anything and pop a wire loose.
So this is like the Teflon tape you get for plumbing?
No. This is Teflon sheet instead of
sheet.
sheet. Okay, let's call it sheet. It's, I don't know, it was like 10,000 stick, McMaster car, razor blade, was cut it on a thing, and that was the strips we used. You see it kind of clamps it. I think the clamp is on the other side, and that's the side that was free because we slid it on like a sled. Yeah. So there we are putting that clamp on to go in the oven to bake, and it baked overnight. And that was another thing. We were really careful, and you might know this, to not have an oven overshoot because there's a lag in the temperature thing. We wanted to make sure we didn't like going to 300. I tried to talk him into going to 250 because the polyimide people says, yeah, you can bake it to 250, just do it an extra hour or whatever it was. And LIGO says, oh, no, I don't want to do that. But I said, if it fails, the first one fails the high pot test, we got a meeting coming up. So we're gonna figure something out. I can't keep making these, So, but it worked. And of course I did testing in my laboratory. I wound the wire around some aluminum and baked it to 350 and then tested it, looked at it on the microscope, and it smashed the polyimide, but it never did leak. We dip it in salt water, it didn't leak. So we're almost done. Let's see. So then, here we are pushing some wires around with a Teflon probe just to make it fit. You can see it's clamped on that end and it slid from that way, but it's already clamped. It's just pushing stuff around, getting it just right before you put it in the oven. And that's that nice lamp again. It actually worked great. Oh, okay. So there's a stack of actuators, space taker uppers, and that's the testing, the final testing unit to make sure everything's right. And I think that's about it. We're about done there. Yeah. Yeah, they are. Ouch.
So how long did all this take?
Well, all the machining and stuff took a year or something. Plus there was delays and all this stuff, getting the magnets in, because the magnets all had to be installed in the plate. And that's another thing with these magnets. You just can't lay them out because you get a ball of magnets. So they shipped them in a little cardboard box, which I'll show you with foam. And we did make just cardboard. It was spaced enough so they would stick together, but they wouldn't be so close that they would smash the stuff. But that's where we broke another rule, because we put it underneath the curtain and opened it up, took the magnet out, went and installed it, 4 feet away, put the cardboard back under the curtain, and did our best to keep the cardboard low. But that's what you have to do when you have 28 times 16 magnets.
These are neodymium magnets?
Samarium cobalt, because they have to be baked. Because this thing gets dipped again in IPA, washed, and then baked again. And then goes in the RGA to make sure before it goes in vacuum.
So you were almost like living in the clean room at LIGO.
Yeah, it was. We spent 3 the first time we bailed early because we had to go remake some tooling. So we did one and let's go fix some stuff. So that was like 5 days. And then the next time was about 10, and the next one was about 7 days. Spaced about a couple of weeks apart or something like that. Just to go figure. The last two I think were just a week apart, just to go home and figure it all out. So anyway, there's a stack of these things, and they all had to be torqued down. You know, Trent did a lot of the final assembly on everything. Let's see what's next. Okay, and here's what you get. That's the signals. You've seen this before.
Oh yeah, these are the
That's the
gravitational
first
wave.
one. That's
Yeah.
the first one.
Mhm.
That's the first one. And I think I got the next picture as yeah, and that's the other picture. But that was a 20.
Those are gravitational wave signals, right?
Yeah, that's the 2015.
Oh, yeah.
Yeah. And that was another thing.
Yeah, this is like the holy cow, it works.
Up-to-date results.
Well, I've been working with them for like 23 or 4 years.
I'm sorry, do you have any before and after your upgrade results? 'Cause you did a thing.
All I did was make the upgrade is squeeze light. If you want to go look and see what squeeze light is, good luck. I could not. Anybody know?
You
how it
don't
works?
understand my question, but okay.
No, I don't. The upgrade, I think it almost doubled it, but this was just the suspension,
Yeah,
part of the suspension for the squeeze light stuff.
did your suspension work? You replaced all of these actuators.
Oh yeah, they worked before they went in vacuum.
Did they,
Yeah.
did they make an improvement to what was there before?
Oh, no. The once you get these things built, they pretty much work the same.
So the reason for
They needed
changing
extras. They needed
They
extras
needed extras,
for the
okay,
squeeze light cavity.
got it.
Right.
Okay.
28,
Right,
28 extras.
right.
And they may
Okay.
need some more because India, there wasn't enough built for India. So if India wants to do the squeeze light, the LIGO India that's coming up, they're gonna need some more. So, but we know how to do them now,
Yeah,
if I can remember. But anyway, yeah, it is pretty interesting. But there's so much more to, I mean, this was just a suspension. And this is, Howard said, can you talk about something? I thought winding the coil might, be something everybody was interested in with the direct drive motors and the magnets too. So the only reason to use samarium cobalt is because of the bake temperature, not the power. They're weaker than neodymium. And of course they're baked and plated with nickel, the magnets, because they go in a clean room. And that was another thing. So the procedure was for LIGO to get the magnets in, clean them, return them to the vendor to be installed, of course. And I don't know how they did 300 or whatever it was times 16 magnets, how they cleaned them. I just don't know. Because the guy retired. You just can't put them on a tray, right? I mean, you get a ball of magnets. You can't they're all wrecked. So I came up with this idea. It was during a LIGO meeting. I said, wait, you're going to clean this thing again after, huh? Oh, yeah. Okay. Well, it said, oh, hang on. So I called the magnet place to just stop because they were just about ready to start magnetizing. I said, just stop. Don't do anything. I'll call you back. So I got with LIGO. I said, how about this? How about if we get the magnet company to clean them to your spec, ultrasonic, DI water and IPA, and then bag them clean, make a little clean area, and then magnetize it. And they're like, you kidding? Can that be done? I said, well, we're going to find out because now LIGO doesn't have to handle magnets. Right. So I called up the guy. And so I bought them a ultrasonic cleaner. That's what I wanted to get it back. But they set up a little area and they did it and magnetized it in the bag. So it came in a bag, a double bag, in a styrofoam and a little cardboard box. And they were clean. And I didn't worry about it because LIGO's going to clean it again and then RGA it. So I'm thinking, oh, yeah, what could go wrong? and actually it worked.
What's RGA?
Residual gas analyzer in vacuum, so they peek it, bake it, and they look and they smell it and see if anything's coming off. Because if it outgasses anything. And that was another question. I said, what about the bubbles trapped in the polyimide? You're gonna have bubbles, right, of air. They said, well, we tested it. It's not a problem. Well, I'm the one that's gonna get the problem when but apparently if there are bubbles in it, they don't leak out the polyimide. Because I would have thought that it would be like a virtual leak forever to have a little tiny air bubble, leaking through the polyimide. But yeah, so it was so yeah, I didn't know anything about winding coils, but I learned quick. So anyway, any questions, anything? I think that's about it.
So you said the magnet manufacturer, they shipped them
Clean.
and LIGO still have to clean.
No, that was the reason. They didn't have to handle loose magnets. Once they're installed in the plate and in the actuator, the field is kind of contained in the steel, right? So they can take the actuators and put them next to each other and they don't stick. So they clean the actuator again before they put it into the additional, it's a low temperature bake, I believe, for the analyzer. See if and that's the final check clean before anything goes in vacuum. And they do that with everything they can. The stuff they can't, like the chambers, they ship it somewhere and it gets clean. I don't know how they do it, but they chemically clean it and seal it and return it. And it's safe to go in vacuum. So.
I have a question about the physical space where these new actuators went. Did it make something longer, or was it like an add-on room, or what?
It was they added a tunnel, and I can't remember how long it is, 100 meters, 300 meters or something, on the inside of the thing and this was for the chamber on the end to suspend it. And they did not want the hydraulics. They said, no, we can do it all with this. So that's what they did. And it has to do something with squeeze light. Anybody welcome to go read about it and let me know next year. Good luck.
Is that light fresh?
What?
The squeeze light, is that
fresh, yeah.
Fresh squeeze light?
You can read about it, but it's like they give up some momentum to get a position, measure that really good, and then they give up the position to measure the momentum, measure that, and now they can combine that so they can increase I think it's the noise lowers, I think.
The quantum.
Yeah.
I never heard of it.
I heard they're taking measurements down along to the scale of the Planck length now.
Oh, that's right? Well, yeah, but they can only read they look at the dark fringe and they look at photons coming through. But this is so complicated. I don't think there's any one person that understands the whole thing, but it was, I mean, I tried to read about
There's a Nobel Prize for that.
Yeah, but this was just a little nothing actuator, and it's space taker upper, right?
Yeah.
And it's another thing too, with this high pot test to 500 volts. I said, well, how much this thing's only good using it is operating at 28 max. I said, can I do 250? Because I was really concerned about it. And there was a few other engineers says, yeah, it's just silly to tempt it to fail, because once it breaks down, you got to unwind it. And I didn't know how to strip the polyimide. If we had to unwind one and strip the polyimide, I don't think you can, because it's polyimide. So I think I thought we'd just have to paint over it, but now we lost some dimension. So we might not get as many winds on it. And then I said, well, let's go look in the control room and see what they're operating at. And their operational voltage is really low because they don't want to put a lot of energy in. And I think that's why that copper piece was on there, was to suck some heat out, or easily, or to get the heat out if there was any in there. But it is pretty remarkable, yeah. But anyway, 28 actuators and 30 bobbins later. So they got extra bobbins because you could easily damage one. You know, if you broke a wire or something like that, if you scratched it, you could just put some polyamide on it and rebake it, I guess, or just leave it. As long as it's not touching anything, it should be fine. But but anyway, that's it. Any questions on the
Any questions out there, Zoomies?
Oh, they all left.
How much does it cost to make one oil well?
Oh, the magnets were expensive. The steel plates, I got them to size, and all we did was drill the holes. So there was a lot of that.
Are you planning to make a gravity
The-
wave observatory?
The polyamide was $850, and I tried so hard to get them to sell me just a little bit. And no. So, I think each one was around. I'd have to do some math because we had extra charges for the engineering. I don't know, 12,000, something like that. Just one. Yeah.
Did you make a profit?
Yeah, we did okay. We did okay. But it was a lot of work trying not to fail one and doing all the unwinding and looking for what failed. Because I wanted to find out what failed. Drain lock nets. I want to find out, right?
Before you do it.
Because you know,
You had 100% yield on your.
they all made it, all 30.
Excellent.
All 30.
Good
And
work.
I sent an email back to the engineer that had failures for 100% failure rate for 2 months. I never got a reply back. So, yeah, none.
No?
But I did find a technician that actually physically wound most of the 300, like 95% of them. And she lived in Slidell, is where I used to live, a couple of miles away, because it was right close to LIGO, was where PSI was. There's a little space hub there because of Stennis Space Center and stuff. And I called her up and I learned so much more from her than I did. And that was her job. Her whole career was doing technical stuff like that for whatever group needed it. And she might have even been contract for like Stennis Space Center, they need technical, technician stuff. And I learned more from her talking to her for a few hours than from the engineer because he didn't do the work, and because I guess the structure was so layered, the information from the technician, she might have been allowed to even say anything, just build another one and not even study it. Just why actually she did it with a foot pedal. I said, how did you do that? But she apparently got good at it. Because she did almost 300 of them or something.
Yeah.
So, or maybe, probably more than that because of the failures.
Yeah.
She might have done 400 or 500.
I wound some coils on Dan's coil. And the last few look a lot better than the first.
Yeah, but it wasn't 20 gauge. The heavy wire is really hard.
Yeah.
Because you got to get to the end. You want to cram it. When do you want to stop trying to get it into you really want to cram it in that spot? We look at it and say, no, let's go back. So we go back the other way and try to flip it over to the next layer because it drops into the hole. And then you end up on the end and it's like, oh, we want to back up, and sometimes we did. We backed up. Somebody just backed up and we did it and went back and there's polyamides all over the place.
If the end was full of copper.
Oh no, we had measured pieces cut out.
Okay. So
And those little pieces, those little coils on the bottom shelf were the leftovers. And we never did run out. We made sure of that. And yeah.
You can't just exactly solder an extension on.
No.
Coiling.
No. Oh, and that wire was expensive
Yeah.
too.
Yeah.
And that's why I didn't want to make a mistake because now you got to buy. I dropped 3 magnets, putting them on. It just because I had a little spot on the surface plate that I just wanted to with IPA just to knock any points off of the nickel plating because I was having trouble sliding it on the nickel plated steel. So I just did that, and a few times it dropped under the steel and I can't use it. And that's what that one is over there. It's one that fell. Perfectly looks fine, but I can't put it in. So the magnets were like $60 a piece or something. So, but anyway, it is an interesting project. And just hanging out at the observatory. Not many people were there. That's kind of fun when people were there, but there was just a few people there because of the COVID. And they quit observing. And I said, well, why didn't you just keep observing? Because it's set up to run remotely. You could run it from your house. Just log in and just keep everything locked, collect data. And they realized that after they stopped for the upgrade, they may have, I don't know. But it seemed like that would have been easy to do. But, nobody knew what was going to happen, when it first started. So when they first went on these lockdowns, they sent everybody home and shut it off, except for the critical, keeping the vacuum up. And I think stuff like that. But it's if anybody's out in Eastern Washington, they have a visitor center that's really nice. And
Is it still out on site?
yeah. So they made a new one, which I haven't been to the new one yet, but all the old stuff is in the new one that was in the lobby. But they were moving dirt around. We were just leaving. They were just starting to build it. And yeah, it's pretty neat.
Okay.
Yeah. So anyway, I guess
right.
that's it.
All right.
Got any
Thank
questions?
you.
Hold on.
That chair.
Since nobody's going to see this.
Okay, so that's the end of today's morning session. And yeah, pretty close to on time. So we're going to take a lunch break until 2:00. So tune back in then, and we'll have the last few presentations and our final wrap up. So thank you to everyone for